Well, on behalf of all the organizers, it's my pleasure to welcome everyone to Elliptics and Beyond, which we're putting on with support from Mines Institute for Theoretical Physics, the Niels Bohr Institute, and CERN. We've got an exciting lineup of speakers this week, and the full schedule is on the Indigo page, so please go check that out. But I also wanted to highlight before we get started that we also have a virtual conference dinner scheduled for Tuesday night at 7 p.m. Central European time. And we encourage people to come even if that's not naturally dinner time in your time zone. There'll be some more information regarding that forthcoming. In addition, starting tomorrow, we're going to have organized discussions at 11 a.m., also Central European time. And these will be mainly focused on the topics covered in the talks on the previous day, but also more general topics. So we encourage you to join us there. And again, there'll be some more information on those talks the day before. In addition to the organized meetings, we have set up a Slack channel where we can discuss at our leisure, even if we're not on Zoom. You should have gotten an email about that this morning with a link that you can sign up. We encourage you to, or actually would really like you to use your real name when you sign up, just so we know who everyone is. And then before we get started, let me just go over some guidelines for how we'd like the talks themselves to go. So instead of directly interrupting speakers, we would like to have questions go through either the chat box or through the raise hand feature. So either you can type your question directly into chat and one of the organizers will present it for you at an appropriate time during the talk. Or if you click on the participants button, there's a raise hand feature and we'll be monitoring that as well. And if you raise your hand, we encourage you to put on your video when you ask a question, just so we can see who you are. And we'll be using that for questions both during the talk and at the end of each talk. So with that all said, it's my pleasure to introduce our first speaker, Ruth Britto, who will be talking about the diagrammatic coaction.
Hi, thanks for the introduction. Great, so I'm looking forward to an exciting week. It's my first time in this series, as I've been very gradually approaching Feynman integrals that involve elliptic functions. So my thanks to all the organizers for bringing us together online this week. Here I'm going to present work done in collaboration with Samuel Abreu, Claude Dur, Enan Gardi, James Matthew, and my students, Ricardo Gonzo and Martijn Hidding. We've been working towards formulating an algebra on Feynman integrals with the structure of a coaction on their diagrams. So we're looking at Feynman integrals as they're typically computed in dimensional regularization as a Laurent series and the dimensional regularization parameter epsilon. So for the simplest Feynman integrals, including all of integrals at one loop, this expansion is given in terms of multiple polylogarithms. And there's a well-known coaction on multiple polylogarithms going back in its earliest forms to the work of Goncharov, and then refined by Brown. So based on that, we've conjectured a corresponding coaction on Feynman diagrams, which can be understood in terms of graphical operations. At one loop, we have a pretty good handle on it. There's an integral basis for which the coaction on the multiple polylogarithms is simply related to the graphical operations of pinching and cutting the original diagram. Now at two loops, various new issues arise in trying to formulate such a diagrammatic coaction, including, of course, the first appearance of elliptic functions. And why do this? Well, the coaction is interesting in one respect because it's very naturally compatible with discontinuity operators and differential operators, both of which are heavily used in various ways of evaluating Feynman integrals. So although we haven't outlined the method yet, we hope that understanding this algebraic structure will be potentially useful for computations. So here's just a first example. So I'll explain this all later, but here's just an example of what the diagrammatic coaction will look like. So this delta, here, do you see the cursor?
Yeah, we can see that.
Yes, okay. This delta here is the coaction operation. So it maps one diagram onto a linear combination of pairs of diagrams combined with the tensor products. And the first element in each pair is related by contracting or pinching away propagators, right? So here, say this propagator has been pinched away, so a triangle becomes a bubble. And the second element in each of these terms is a generalized cut of the original diagram. So I've just marked some propagators to go on shell. Now the point is that each of these diagrams can be evaluated in DimReg in terms of polylogarithms or multiple polylogarithms in this case. And if we do that, then the coaction on multiple polylogarithms is consistent with this operation on graphs, which I'm just showing this. I'll show the simple examples of the coaction on multiple polylogs. So the discontinuity operator will act on just the first elements in the polylogarithmic coaction, so that's known. So in terms of the graphs, it makes sense that the cut integrals, which are the discontinuities, are appearing in the second elements. That's sort of what's left, what just comes through when you act with discontinuities in the first entry. And likewise, differential operators act just on the second elements. So it leads to differential equations. Okay, so what is a coaction? Time to introduce some mathematical definitions. It's an operation in a bialgebra. So to review, an algebra is a ring with an addition operation under which the elements form a group, and multiplication operation with a multiplicative unit, and which is also a vector space over some field. And for us, the field is always the field of rational numbers. That's an algebra. A bialgebra is an algebra with two more maps, of which we're focusing on the coproduct. And there's also something called the co-unit, and they satisfy the following axioms. Since we're very interested in the coproduct, we're going to focus on this one here, which is co-associativity, which means you can apply the coproduct, right? And then you get something in this space, which is a tensor product, H tensor H, and then you can apply a further coproduct on either the second entry or the first entry. And so the two ways of doing that will lead you to the same result. Then there are some other axioms related to the co-unit. Now, okay, that's coproduct. Coaction now generalizes this coproduct to a tensor product of two different spaces. Here's a simple example. I love this example. It's called the incidence algebra. It's a very simple example of a bialgebra, which turns out deeply related to the algebras we come to when looking at Feynman integrals. So let's look. The elements of this incidence algebra are just pairs of subsets of some finite set. So it's like the set of elements labeled 1 through n, and it can have subsets. Those subsets can have subsets in turn. And so a pair will be an element. So to make this a little bit clearer here, instead of writing out all this subset as subset of another set as an element, for short, I'll just take the subset 1, 2, and then I select some further subset to color purple. Right, so instead of this element, I just write it a bit more neatly this way. The empty set is a subset of all sets, so nothing is colored. The empty set is a subset of itself. That's just denoted by a star here. And what are the operations? So multiplication will just be a free operation, and the coproduct is given by this. So coproduct of some element, right, nested subsets will be a sum of all the ways of inserting subsets that are contained in between S and T. So for example, here are some coproducts in the incidence algebra. So empty set is a subset of 2, and there are 2 subsets in between the empty set and 2, namely the empty set itself here, or 2 itself. That gives you 2 terms. Likewise for all the rest. And we can verify that this definition satisfies all the axioms of a bialgebra. So I say, okay, for completeness, I give the co-unit. The co-unit is also very simple in this case. It's just 1 if S equals T, if it's the same subset, 0 otherwise. Now, I think this is the last we'll see of the co-unit. We won't really be using that explicitly. We'll be using the coproduct, or rather the coaction. So it's coming back to the difference now. If H is a Hopf algebra, well, okay, let's just say bialgebra. We don't need a full Hopf algebra. Then an H comodule is another vector space with a map rho satisfying these relations. So this is really the coaction. Rho is the coaction. Delta is the coproduct on the original bialgebra H. So this is just what I was saying before, but you'll have an element, you have two distinguished spaces. Anyway, this is a distinction we will mostly gloss over. In this presentation, we continue to use delta for coactions of bialgebras. And the difference between the left and the right space will be very subtle. So now we can directly apply the incidence algebra to a graph. So recall this example from the incidence algebra. So this is the empty set as a subset of a two-element set. Right, so there are 4 intermediate subsets giving 4 terms. For graphs now, consider just the set of all of a graph's edges. That's it. And we're looking for nested subsets. So if S is a subset of T, then we draw the graph with all edges contracted except for those in T. And of the edges remaining, we distinguish the ones in the smaller subset S by giving them a decoration, which is a mark across the edge. This looks a lot like our first depiction of the incidence algebra. And this equation here, so this is a direct mapping of this equation onto just edges. Right, so I'm not even using the graph structure. It's just really the set of edges. Okay, I'm using the graph structure to show how to contract the edges that aren't being used. And for graphs, the empty graph is just set identically to 0 rather than having an element, which is an empty graph. So this is starting to look like what we can do with Feynman diagrams if we start interpreting these marks as cut propagators. Now we want to evaluate these diagrams and compare them to the coaction on multiple polylogarithms. So let's now review multiple polylogarithms and their coaction. These multiple polylogarithms are described as iterated integrals. Right, so at each step in the iteration, you can introduce a denominator, which is linear in the integration variable. As examples, this includes the logarithm itself, powers of logarithms, classical polylogarithms, and it has a grading by the weight, transcendental weight, which is the number of iterations in this integral. These multiple polylogarithms are closed under multiplication via the shuffle product. So here the summed over the orderings of these parameters, preserving their relative orderings. And here are just a couple examples of the coaction. So there exists a coaction, which in turn, in fact, is graded by weight, which maps the multiple polylogarithms into functions of lower weight in addition to themselves. So here are examples with products of logarithms and classical polylogarithms. Also notably, acting on a transcendental constant, I pi, you get I pi tensor 1. The coaction has become a useful tool for working with multiple polylogs in Feynman integrals. It makes use of the weight grading and it exposes relations among different multiple polylogs, which allows for simplifications. Now the coaction on multiple polylogs can be written in a form reminiscent of the incidence algebra. We sum over subsets of the parameters appearing in the functions. So the first element in each term has only the subset taken as parameters, so there's less iteration, and the corresponding second element has the full set of parameters here in the list of what you put into the integral, but the integration contour is changed. It's integrated on a contour which encircles this subset of residues in order. Now there's also a coaction for elliptic multiple polylogarithms. This was spelled out in a paper by Britto, Dulac, Penante, and Tancredi. it would take too long to define everything properly here, and I won't be showing an explicit calculation with it anyway, so I'm just going to summarize the basic idea of the construction. So consider again the multiple polylogs. Another way to approach their coaction is to go through what's called the symbol. Consider the total differential of a multiple polylog. Because of its iterated integral structure, it can be expressed recursively, as seen in this formula. We can then define the symbol, which is an element of a tensor algebra whose entries are rational or algebraic functions. Here, so we just kind of take off the differentials, put in a tensor product, and construct something like that iteratively. Now this symbol can be understood as the maximal iteration of the coaction. So after constructing a symbol, we can work on lifting it to a coaction, which is a more powerful tool than the symbol, although both have been very useful. So we, or rather these people, try the same approach for elliptic multiple polylogs. Now, what are elliptic multiple polylogs? There are a few different versions of this kind of concept with different pros and cons, but this is the one that leads to the coaction that we're studying and using. So here, this is also defined by an iterated integral, but now you see there are a lot more parameters involved, and these integration kernels here, these come from, so tau is taken from an elliptic curve, and the kernels then are constructed through a generating function, which is constructed from Jacobi theta functions. So this definition as iterated integrals, I should say, I mean, the other definitions are also various kinds of, well, there's another version which is iterated integral. So perhaps something similar could be done, but for us, this is sufficient. This iterated integral structure leads to, similarly, to a recursive total differential formula. Just copied here. There are a lot more definitions involved, but this is just to show that there is a similar kind of formula. These omegas are differential one forms, which are fixed. So this leads similarly to the definition of a symbol, and then eventually a coaction after many, many more definitions. And I refer you to the paper by Britto, Dulat, Panente, and Tancredi for the extensive details. Okay, now we'd like to see how we can use this in diagrams. So the first step is to take a good look at one loop integrals. So several years ago, we proposed the one loop diagrammatic coaction, which is this idea that the coaction on one loop graphs, or rather a basis of one loop graphs, which can be defined by just pinching and cutting the graphs, subsets of propagators, when evaluated by Feynman rules in dimensional regularization and then expanded order by order in epsilon, the proposal is that that will agree with the coaction, the known coaction on multiple polylogs. Now, in order to interpret diagrams as integrals, we need a little bit more information. At one loop, we take them as scalar integrals, right? So if I just give you a picture like this, you can say, okay, it's one loop, but how exactly do I construct the integral? We take them as scalar integrals, and we have to know in which dimension we're evaluating them. So based on the number of propagators, we choose the dimension, according to this formula, whether n is even or odd, so it's always in an even number of dimensions, minus 2 epsilon. And this basis is nice because it does give a basis of one loop integrals, and the functions are pure when normalized by the leading singularity. The very simplest example we could look at then is the tadpole, or the very simplest one loop integral. So this, according to the formula on the previous page, this should be evaluated in 2 minus 2 epsilon dimensions. We then write this formula from the incidence algebra. Right, so this is just an operation on graphs. The idea is whatever is not pinched, whatever propagators are still visible here, will be cut in the second entry. So there's just one propagator. If you pinch it away, there's nothing. So there's only one term with that visible. And then because that's still there, it has to be cut here. Okay, so we know what the tadpole integral is in 2 minus 2 epsilon dimensions. We also know what its maximal cut is. It's easy to evaluate in any number of ways. And it's also, so given these formulas, it's easy to verify that the epsilon expansion is consistent with the coproduct on logarithms. For more complicated examples, we'll need to define our cuts very carefully. And in fact, for the diagrams, we'll find a specific modification that we need to make to the naive construction from the incidence algebra. But first, I'd like to talk about how to define cuts. So we define generalized cuts as residues. Instead of putting delta functions into the integrand to put propagators on shell, we're going to change the integration contour to encircle the poles of the cut propagators. This resembles the contour modification that we saw for multiple polylogs. We evaluate the cut integrals only modulo I pi. This is enough to be able to use them in the second entries of the coaction, which is where they appear, because the coaction for multiple polylogs is also, well, it's on the space of multiple polylogs taken modulo I pi. So this is coming back to this, for us, rather subtle point about the distinction between the coproduct and the coaction. One way to think about them as separate spaces is understanding that the uncut, or that the second entries can be interpreted only as cut integrals, or in terms of the polylogarithmic coaction, that they have to be taken modulo I pi. And this is related to that formula that the coaction of I pi is I pi tensor 1. So this freedom then also allows us, when we're doing this, to choose convenient and independent integration regions. So we're not too bothered about the details of the kinematic regions. Cut integrals can be understood as discontinuities. We can see this precisely in the framework of homology theory, which has other applications that are useful for us here. So the proper definition of cuts, we can invoke homology theory to understand the integration contours. And this leads to relations among the various cuts. So here we understand that the kinds of residues that are appearing in the integrals are Leray residues. A Leray residue is defined as follows. If you have a differential form here and you're looking for a residue around s equals 0, then you try to decompose your differential form such that you see a ds over s appearing, and then together with some other forms that are regular on that singularity. And then you read off the residue as this coefficient, if you will, psi restricted to the singular space. Applied to cut integrals, so we're taking residues at a singular locus. It's the locus where the propagators are going on shell, the kinematic space where those on shell conditions are satisfied. And so the equations shown here at the bottom show that the Leray residue of the integrand can be recast by Stokes' theorem as an integral of the original integrand over a contour encircling the pole, a tubular neighborhood. Now, if we think of all generalized cuts and all the ways to construct these contours encircling poles, we're confronted with the existence of a pole at infinity and its residue. Now, at one loop, there's a powerful theorem from homology which shows that it's enough to consider the cuts of visible propagators. That's this decomposition. So here, a contour encircling the pole at infinity turns out, this is just the result of the theorem, that it's a linear combination of these other contours, the one without infinity with some free factor, and then all the other ones summed over C as rather X propagators, a set of propagators that include all the cut propagators. And there's a difference here appearing depending on whether the number of cut propagators is even or odd. So thinking ahead beyond one loop, we know that this geometry, this homology analysis is going to get very complicated because of the geometry of multi-loop integration. But it turns out we can still largely rely on the one loop results when we integrate one loop at a time. So let's return to the simple one loop examples. Moving on to the next example, which is the bubble. The diagrammatic formula that turns out to be correct is the naive one. Well, the naive one is this, right? We just have all the pinched diagrams here and then the corresponding cuts here. But there are some extra terms that we call deformation terms, which are the last ones here in the parentheses. Now, to understand where these are coming from, I've rewritten this exact same equation in terms of integrals here. This is just shorthand. So now this omega just means the integrand with propagators 1 and 2. And the contours are also labeled by which propagators are being cut. Right, so here nothing is being cut, this gamma empty set. Okay, so just rewritten everything in integral form. And now by combining these combinations, right, so these cuts are just different contours. We can also combine the contours linearly. Now it turns out from that decomposition theorem, okay, so what's missing here is just this third line. It's very similar. This is not an infinite series, just a slight shortage of space. But we can see here, by combining this contour with this contour, we get exactly this combination, which is just the contour related to 1 and the pole at infinity. And now, see, now we even have space to bring in this extra term. The last term is just this combination, which is a contour related to the pole at propagator 2 and infinity. And then it just happens to be mapped back to this additional cut here. Okay, so this is the same formula from the previous page. So we have a basis now of integrands and corresponding contours. So now we can see, instead of this being puzzled about where these terms are arising from, we understand exactly how to pair the terms in this coaction. When you have the propagators that are not being pinched away, then in the second entry, you encircle those residues, right? So you cut those. But if it's an odd number of edges, then you add infinity. And this distinction between odd and even was exactly the one that was already visible in the decomposition theorem that comes from understanding homology properly. So this is the only modification we need to make. And we believe that this pattern holds for all one loop integrals in generic kinematics. And then you can take massless or equal mass limits as desired carefully. And we've checked many examples of those. There's another comment about these pairs of integrands and contours is that at leading order and epsilon, they are dual in a way that can be expressed at this condition, that at leading order and epsilon, this matrix is the identity. The diagrammatic operation can also be applied to cut integrals. If a propagator is both cut and pinched, then the whole diagram is set to 0. So you're just left with whatever you're left. So in fact, you can just apply cuts to the previous formulas. Like you can take this here and, so I'm just showing a maximal cut of a triangle, but coming back here, if you were to say to cut both propagators, that would just leave you with this term, because here you're trying to cut something that's already been pinched. So this would be 0, this would be 0. And that would leave you with a group-like formula. So the maximal cuts are group-like in this sense, that their coaction just gives the same thing times itself. So to summarize what we find beyond one loop, we have some examples of a similar structure, which I'm coming to. Since it's harder to understand the geometry and perform the computations, we do not yet have a general prediction, but we are working towards formulating one. And this we're heavily inspired by Brown's motivic Galois coaction on Feynman integrals. Now, of course, given the subject of this week's workshop, we're especially interested in the appearance of elliptic integrals. But now, before we look at the two-loop examples, let's just review the general framework. As we're looking for coactions on various integrals, we're looking for this type of integral formula. Right, so the first entries in the coaction have different integrands, and the second entries have different contours. So this is a lot like just inserting a complete set of states, some kind of basis here. And this formula is meant to be applied compatibly to Feynman integrals with cuts. So that's like what I was just showing for the bubble. Also for multiple polylogs and elliptic multiple polylogs in the epsilon expansion. So that's like the illustration of choosing different contours there. That's the same kind of formula also applies. And finally, also for unexpanded hypergeometric functions using intersection numbers. So without expanding an epsilon, Feynman integrals can be expressed as generalized hypergeometric functions. We found in some cases that it's possible to construct a coaction on hypergeometric functions directly that's consistent with its expansion in multiple polylogs. We have some preliminary results and are pursuing that further, but I won't discuss that here. And again, I remark that the coaction on integrals resembles the incidence algebra. All right, so at 2 loops, what we have are some examples. Let's start with some examples that are still polylogarithmic. So here's the sunrise with one massive propagator. Now at 2 loops, we have a new feature, which is that you can have multiple master integrals appearing in the top topology, and they must be considered together. So here, for this sunrise with one massive propagator, let's choose this basis. These integrals with the prefactors given here are pure in 2 minus 2 epsilon dimensions. Typically, when you're thinking about the sunrise, you might take the second master integral to be one with a squared propagator, but here we've written one that has a numerator instead. They both have a closed form expression in terms of the Gauss hypergeometric function 2f1. So we can compute the coaction. We can do this to all orders, actually even with for 2f1, and we find the following equations. Well, so what I'm showing here, I'm just showing the pictures now, but you can actually do this to the multiple polylogs and the expansions, and the point is that these diagrammatic equations will be true when mapped to the multiple polylogs if everything is defined properly. So let's make some points here. So notice that now both master integrals, right, for a given master integral, its coaction will involve terms with both of the master integrals appearing in the first entry. They're being mixed. This makes sense when we think of the differential operators acting on the last entry, because both the masters satisfy the same differential equation. It's a coupled system, so we're happy to be seeing both. That's what should happen. In this example, now there are nothing is being pinched in the first entry, right? Everything has the same shape. This is just an accident of this example, because you can imagine pinching a propagator, but then you'd be left with a double tadpole. And now because 2 of the propagators are massless, and massless tadpoles are 0 in dimreg, there is nothing that's non-zero that you can still write down here. So that's why this is quite simple here. Now, corresponding to the 2 masters in the top topology, the space of cuts, actually all cuts, has dimension 2 as well. And there are 2 solutions to the maximal cut equations. So while we could consider other generalized cuts and try to feed them into this equation, it's not necessary because there are linear combinations of these. And in fact, we prefer here to take for our basis 2 independent maximal cuts, because that allows us to continue the same pattern we observed at 1 loop, where diagrammatically, wherever a propagator appears that's not being pinched, that same propagator is in some sense being cut in the second entry. So now, just as at 1 loop, we need to understand precisely how to compute all these cuts. So let me just show a bit about the 2 maximal cuts. This is showing how we set up the cut calculation. So we integrate 1 loop at a time. The order shouldn't matter, certainly for a maximal cut, but for other ones, you also might want to check the order doesn't matter. So the first loop here is a familiar 1 loop calculation, maximal cut of the bubble. We know how to do that with our definitions. After that, then we still set up another integral where we have to take 1 more residue of a propagator. Now this residue isn't enough to completely fix the integral. There's still some freedom left in choosing an integration contour over the last integration parameter. So here, right, I haven't specified the contour. We can choose the endpoints of integration from among the branch points of the integrand. So we've got 3 factors here. There's also a branch point at infinity, along with the zeros. And the possible choices give 2 independent results. If you recall the Euler integral formula for Gauss hypergeometric function 2f1, you'll recognize that here. This is a 2f1, as expected. So this is the same analysis then of integrating between branch points that's used by Aomoto to generalize the notion of hypergeometric functions. Anyway, so here it's consistent with 2f1. We get 2 independent integrals. And here in computing cuts, we're also still always working modulo I pi. Okay, so then coming back, so we just choose to define 1 and 2. Actually, the best we could say at this point is that we choose the 2 independent contours such that this formula works and that there exists a choice of basis of the maximal cuts such that this is exact and compatible with a coaction on multiple polylogs. Here's another example. This is also expressible in terms of 2f1 function. So this diagonal box has only 1 master integral in the top topology. But now, so that's this. Now we do have some pinched integrals appearing. You can pinch away a propagator and be left with something, and they appear together with their corresponding cuts. And the cuts here are straightforward to evaluate. And the formula looks very much like the one loop examples, again, in the sense that the propagators that are still appearing on the left are being cut on the right. A more complicated example is still polylogarithmic, but now we come to the sunrise with 2 massive propagators. So I've just drawn our result very schematically here. We computed it, although you can't see from the diagram, we did compute it for 2 distinct masses, M1 and M2 here. So here again, just like in the diagonal box, there is a pinched integral, right? So here's the easy part. And the different colors of cuts represent sort of different solutions to the maximal cuts. Okay, but here there's a pinched integral because there now is a non-vanishing double tadpole. And it comes along with what you'd expect, the integral where you'd cut the 2 massive lines, but also these deformation terms. The deformation terms appear here, just like at one loop where you cut an extra propagator. And so the way we understand this is that these deformation terms are directly inherited from the one loop structure. As you're integrating loop by loop, you consider what the pole at infinity is doing. You map it back to the visible propagators in that loop and keep going. So we've found sort of a choice of the maximal cuts and this cut that make this correct. And for completeness, here's also the coaction on the 4th master integral, the double tadpole, which of course follows from the coaction on one loop tadpoles. Here also we were able to use the hypergeometric coaction on appel F4 to compute these in closed form, or to all orders in epsilon, if you like. So a remark I'd like to make is that pinching propagators in the first entry is not going to reduce the loop order. So we're always still going to get 2 loop integrals in the first entry if we have a diagrammatic coaction. This is in contrast to Brown's motivic coaction where the loop order was reduced. But we don't expect to reduce the loop order. We don't expect to be able to because of the relations with differential equations. All the master integrals are solutions to the same differential equation, so they come with the same, loop order. All right, so now what about the elliptic case? The calculations get very heavy, of course, so we're going to start by looking at the elliptic sunrise, starting with the equal mass case. Now to assemble a coaction, we must compute the cuts, and we have the same kind of freedom in defining cut contours. These cuts can be obtained by direct integration or by a method involving differential equations, which we've used primarily. This uses this a package by Martin Hitting, which he will discuss more on Friday, called diffexp, to transport boundary conditions to convenient kinematic points. So we used a Bykov parameterization and the canonical basis given by Adams and Weinzierl. Here's the basis and the differential equation for the equal mass case. Now in the differential equations, this method of computing cuts, we compute boundary conditions for each of the cuts at some preferred kinematic point. So just find some limiting case in which the integral really simplifies, and you can write it down nicely. And then with great care, you analytically continue to the even more special point x equals 0, where the expansions in epsilon then are observed to evaluate to polylogarithmic constants. Then you can solve the differential equations in terms of iterated integrals of modular forms and continue back to whatever point you like. So here we have actually found a coaction for the elliptic sunrise in the equal mass case, where the master integrals appear in the first entries and cuts appear in the second entries, and which is consistent with a coaction on the elliptical multiple polylogarithms that appear. So that's one of the elements we're looking for that really gets us on the right track. What we have not quite got yet is a diagrammatic version where you have really nice picture where you have the uncut propagators in the first entry, the visible propagators in the first entry corresponding to the cuts in the second entry. And it's not that it's impossible, it's that actually that we have this mess of prefactors and change of basis. So actually we hope to get this into a diagrammatic form very soon. I don't really see an obstacle, but are not quite there yet. Also in progress simultaneously is the case, the unequal mass case. It's not tremendously different. It's a heavier calculation. We have 7 masters, of course, if you in that case, but I have a similar procedure, and we will be looking to that for guidance too, because if the masses are distinct, then you could consider limits to the 1 mass case and the 2 mass case, which we do understand diagrammatically, to organize and to see if there are deformation terms that appear. Because we also know from our experience at one loop that if you take many masses to be equal, it's just harder to see the pattern, right? If too many variables are the same, you can get some coincidences. So we're still working on that and are very excited to see what we're going to find soon. Let me then close with that. That's where we are. So to summarize, we do observe in many examples a coaction structure on Feynman diagrams. At one loop, there's a basis for which the coaction is simply related to pinches and cuts of the original diagram. And a similar structure is emerging in 2 loop examples. The elliptic case is being explored through the sunrise example primarily. There is a coaction involving cut integrals that's visible in the equal mass case. The diagrammatic version of the unequal mass case are still in progress. So the diagrammatic coaction corresponds to the coaction on multiple polylogs or elliptical multiple polylogs in the epsilon expansion. It's important, of course, to understand what the cuts are. They're constructed as residues with final integrations taken between branch points of the integrands. That means certainly going beyond one loop, it's not enough to say which propagators are being cut, right? Because you also have to describe, on top of that, which contour you want to take in which case. The coaction has deep connections to discontinuities and differential equations, which we hope will lead to better tools for computation. And then the final point is just that we have this sort of unified vision of the formula for a coaction, the coaction on integrals, which looks a lot like an instance algebra, which is based on matched pairs of integrands and contours, which we conjecture to be applicable to generalized hypergeometric functions that appear in Feynman integrals as well, which is another direction for exploration, especially in the elliptic or non-polylogarithmic case in general. Thank you.
All right, thank you, Ruth. We can try for a real applause here if people want to unmute themselves quickly. And then, if people have questions for Ruth, we've got a couple minutes because I took up the first couple minutes of the talk. But while we're waiting for more questions to come in. I guess I'm wondering if you had the diagrammatic coaction working at 2 loops right now, what would be the first place you're interested in applying it?
Good question. Yeah, I mean, it's hard to. I guess we would hope then to be able to understand it. I mean, to all loops right away, right? Many of these features that appear at 2. I mean, just the fact of having multiple masters, for example, or having something non-polylogarithmic, or having to make the move to hypergeometric functions, I think would at least allow us to propose some coactions for higher loop orders as well, or even non-elliptic cases, where then we might not even have a coaction on the function. And okay, so then, yeah, if you could do that really diagrammatically, that might then also give some clues into how to set up differential equations.
Okay, yeah, thank you. We also have a question from Niels.
Hi, Ruth. Thanks for a great talk. So I think this is just my confusion, but so if I understand it correctly, you want a coaction on the Feynman diagrams, but it seemed to me that you construct it by looking at the Feynman integrals. Is that correct?
Yes, well, you could say, I mean, naively, when I just first showed the illustration of the incidence algebra, you set it up on diagrams, but it, of course, it doesn't mean anything physically until you say what you want it to do on Feynman integrals, and then you find you need these deformation terms.
Okay, so
let me emphasize, though, that actually introducing the deformation terms actually doesn't really change the fact that it's an incidence algebra. It's an algebra isomorphism.
Okay, so the point is that the coaction on the level of Feynman diagrams is really just a special case of an incidence coaction. Is that what you're saying?
Yes, and of course, yeah. I mean, to see which version it is, you would have to understand something about the physics. So, right, I mean, you can do this purely on graphs with no physical input, and of course, that's. I mean, then you're done, right? That's not very illuminating.
Okay, so the game is then
okay. The point,
yeah,
I mean, it is based on this combinatorial structure.
Okay.
But the point is that then this can be, there's a mapping of the combinatorial structure onto something that's physically meaningful in terms of the functions.
And you want that coaction on one side to be compatible with the one on the other, of course.
Yes.
Okay, thank you very much. That was helpful.
Okay, any other burning questions out there? If not, we've got the Slack channel, and also we'll have the discussion tomorrow. I don't see any other hands raised, so let's give.
May I ask a question? I can actually not raise my hand as I co-host.
Yes. Go for it.
Thanks for the interesting talk. So just maybe a more technical question on the example with the 2 mass sunrise. No, okay, it was the 1 mass one. It looked very symmetric in the 2 contours. That was on the page 17. Was that a generic feature or just an accident because of the simpleness of that example?
Symmetric, you mean that there are, yeah, I mean, if there were, I mean, there could be prefactors that are absorbed into the definition of the into the cut. But no, actually, I think so these are just 2 maximal cuts. I mean, I'm sure that there isn't really a symmetry here because, of course, these 2 masters are quite different, right? One has a numerator and the other doesn't. So it's.
But
so it's just true. So, I mean, the point is that each of those masters has its corresponding contour. And yeah, so it's beyond that. No, okay. So yes, and it does work out nicely, of course, that these sort of cross terms don't have any additional factors. I can't say it's due to symmetry. No, so that goes. I guess that just goes back to this kind of formula. There is some kind of basis or 2 dual bases. So once you have identified a basis and then its dual basis, then this kind of structure does give a coaction.
Okay, thank you.
Okay, thanks again.
All right, let's thank Ruth again, and then we will move on to Roman. Great, we're happy to have Roman Lee here, talking now about the symmetry of differential equations for non-polylogarithmic loop integrals and quadratic relations for their epsilon expansion coefficients.
Okay, thank you. I'm actually very happy to present a talk here and to see all participants whom I didn't see for a long time due to understandable reasons. I'm actually a little bit, I was hoping to present a more detailed talk, but you know, it's elliptic stuff is really complicated. So I have something new to say, but not so much, okay? But I hope it will be interesting for the present audience, okay? So first I would like to make a historical remark, which I find very amusing. It is that the polylogarithmic and non-polylogarithmic functions appeared in one and the same journal issue by one and the same author, by Raka in 1934. So what he did, he calculated basically total cross sections or something weighted total cross sections like energy loss for the first process, which is equivalent to calculating box diagrams, two loop box diagrams with in forward kinematics with some propagators cut, and you see in the first paper it is. It is expected, polylogs, they appeared first in the first paper. So in the first paper, he had polylogs. In the second paper, he had elliptic integrals. And also, I would like to note that the form of the second result, if you look at it carefully, it is very contemporary, right? Because you see here iterated integrals and the kinematic dependence on the kinematic variable is only in the upper limit of the integrals that appear. So I was really surprised to see this result that early. And also I don't understand how he obtained it by direct integration. So now, of course, we do it differently. We just usually follow one and the same path. Since the invention of the IBP reduction, we are used to do the following. We just consider a family of integrals with different powers of denominators, and then we construct IBP relations, we do IBP reduction and find master integrals. Then the same IBP reduction can be used to construct the differential equations. And this is what we can do fast and for sufficiently complicated examples. So we can also obtain dimensional recurrence relations, which from time to time are also very helpful. And you will see that they are also helpful for the present analysis. And then we are left with general, we have to find general solution of the, in particular, differential equations. And then we have to find a way to use some direct, so to say, methods like Mellin-Barnes representation, something else, to fix specific solution from this general solution. So what I will talk about mostly is about the properties of the general solution, in particular for the case where this general solution cannot be expressed in terms of the polylogarithmic functions. Okay, let me say a few words about polylogarithmic case. For polylogarithmic case, it is naturally connected to the epsilon form of the differential equation. So in 2013, Johannes Hen made a remarkable observation that if you carefully choose the master integrals, then the differential equation has the form where the epsilon dependence on the dimensional regularization parameter is factored out in the right hand side. So why it is important? Because then you can clearly see that the general solution, which is path ordered exponent, can be expanded in perturbative series in epsilon, and each coefficient is obviously expressed in terms of the Goncharov polylogs. So to summarize, this epsilon form of the differential equations guarantees, so to say, that the solution can be expressed in terms of the polylogs. Okay. Now you know that there are algorithms which are highly automatized. Also, there are some public codes available. I would like to advertise my own code, Libra, which is available by request. I invite you to give it a try. And basically, we have now a tool to decide, to construct the solution for the case where this solution can be expressed in terms of polylogs. And also, we actually have a tool to decide whether a given system can be reduced to epsilon form or not. So basically, what complications can we meet? First, first of all, of course, there is no sense to say about general transformations, because if you allow for any transformations on the system, then of course you can just take this transformation to be equal to this path ordered exponent, and then this system becomes trivial. But then there is no use in this substitution, right? So we have to somehow restrict the class of the transformations that we allow. So one option would be to restrict yourself with rational transformations, right? So rational transformations are those which are given by matrices which are rational in both variable and epsilon. But it appeared soon that it might be not sufficient to use these transformations. You have to use more general transformations. In particular, it is often needed to use the transformations which are rational in some auxiliary variable y, which is related to x via some rational function. So x is a rational function of y, but y is not. And also it is clear that this is some extension of the class of transformation, because the transformations which are rational in x are obviously rational in y, but not the other way around, right? So if you have some transformations which are rational in y, then this transformation is not necessarily rational in x. So this is some kind of extension. Also, you might need, if you solve a big system, then you might need several such transformations and several auxiliary variables. So there is a question of if there is a one variable change which can rationalize all matrix. In general, it is not so. So in principle, you might also encounter complications to express everything in terms of polylogs, even if epsilon form is possible for for this with this extended class of transformations. But usually you don't encounter such problems. You might have in one huge system, you might have several variables, but usually they do not interfere with each other. Once you express everything in terms of iterated integrals, it is usually possible to find rational substitution for each of the integral which appears. And the worst case is that when you cannot find the transformation to epsilon form. So we have managed to devise a criterion of irreducibility. So it's not a question of good luck or bad luck. So you can decide whether you can reduce the system to epsilon form or you cannot. So of course, we all know that in many examples, it is not likely that you can find polylogarithmic solutions for example, for two-loop sunrise graph. You know, we do know the solution, and we do believe, at least, I mean, maybe we even know this, that this solution cannot be expressed in terms of polylogs. In this case, we have to somehow either to extend the class of the transformations or to give up this epsilon form because it's not very useful in this setup. So why it is important to, I mean, what are good properties of the polylogs which are important for the applications and also for the analysis? We basically know all properties for polylogs. We know all information that we know for elementary functions, right? We know functional relations. We know transformations, how to transform the argument. We know asymptotic series. We can differentiate those functions. It is also important for the applications that we can we can devise a fast numerical computation. Basically, you can, for example, use series expansion, and then you can just calculate up to any precision that you need. Also, good properties are grading of this class of functions with respect to transcendental weight. Then we can use this, for example, for guessing the correct function using PSLQ from the numerical result. So we have many good properties. Basically, this is what we would want to know about, also about the non-polylogarithmic integrals. So let us see what we can say about systems which are not reducible to epsilon form. First of all, and I think this is the most important thing, is that we have to consider those cases one by one. So each such reducible case needs special treatment. And this is quite difficult and time-consuming. But up to this, we can say a lot, actually. I mean, for example, we can devise a series expansion up to any order in different points, in particular using differential equations and Frobenius method. We can also devise a fast numerical computation, although we have to, as I said, consider these irreducible cases one by one. So we have to devise some custom codes in general. What is less known is our functional relations. Since we don't know the class of functions, we don't know anything. I mean, in general, we don't know anything about functional relations, and this is what I want to contribute where I want to contribute. So my point here is that there seems to be some non-trivial symmetry of the differential systems for multi-loop integrals. And it is possible to find this symmetry using existing tools. And this symmetry gives gives many constraints, quadratic constraints for the coefficients of epsilon expansions. Also, it is possible to ask a question about the, so to say, generalized form, generalized epsilon form or canonical form for these epsilon irreducible systems. And let me just show you some details. Let me give some simple definitions. This is, I want to give a definition of rational equivalence. If you have two differential systems, then we will say that they are rationally equivalent if there is a change of functions which is rational and which maps the first system to the second. So in terms of matrices which stand on the right-hand side, we have the following relation, usual relation. So we will write that these matrices are rationally equivalent, in a sense that when they stand in the right-hand side of the differential systems, they correspond to rationally equivalent systems. What is good about this rational equivalence is, of course, that monodromy groups are isomorphic. Also, the important properties that we have for multi-loop integrals is that we can clearly claim that the matrices shifted by epsilon are rationally equivalent. Why is it so? Because of the dimensional recurrence relations. Okay, using dimensional recurrence relations, we can easily prove that basically the matrix which stands in the dimensional recurrence relations, it connects the systems which are shifted by with respect to epsilon. So now, in terms of this rational equivalence, the reducibility to epsilon form means just that the system is rationally equivalent to some system which is in epsilon form. There is a natural question. If you have two systems, is it possible to check whether they are equivalent, rationally equivalent or not? And if they are, then to find this matrix T. This is seems to be an important question. And of course, it appears that it is possible. You can just reduce both differential systems to normalized Fuchsian form. And then you have to compare. You have to compare singular points of the resulting systems. You have to compare matrix residues. If something is different, then the systems are not equivalent, obviously. But if those ingredients are the same, then you have to try to find the matrix, invertible matrix, which does not depend on X, such that the following relation holds. This is just a system of linear equations, so you can easily solve them for each specific case and see if there is a solution which is invertible matrix. Okay, so if such a matrix exists, then the systems are equivalent, and then you can just construct the transformation which maps one to another. This is almost obvious, and in order to see that this is indeed so, in particular, this third step may be questionable, because it's not quite clear why you should restrict yourself with matrices which do not depend on X. Yes, but this follows from the proposition of our paper with Andrei Pomeransky. Basically, this proposition says that if you don't want to shift the eigenvalues of the Fuchsian system, of the residues of Fuchsian system, then you are restricted with the transformations which do not depend on X. Any transformation which depend on X somehow changes the behavior of the system near at least one point. Okay, so if the point was not singular, it can of course become singular. But the point is that you cannot allow for X dependence in the transformation if you want to keep all invariant properties like eigenvalues of the matrix residues in singular points, and you want to keep regular points to remain regular, then this matrix necessarily should be constant, independent of X. It can depend on epsilon, of course, but not on X. So now let me define epsilon conjugation and epsilon transposition. This is the following operation. If you have some matrix which depend on epsilon, then you can define the matrix M star, which is transposition of this matrix and replacement of epsilon by minus epsilon. Okay. Then in the same way we define epsilon symmetric matrices and epsilon orthogonal matrices. We can also define epsilon conjugated differential systems. You know that if we omit this change of sign of epsilon, this is just a definition of the conjugated differential system. You have to transpose the matrix in the right-hand side and change the sign, right? But here we define epsilon conjugation. Okay, so you not only do this as usual, but you also change the sign of epsilon. Why it is? Why I need this definition? You will see on the next slide. If you omit for matrices which do not depend on epsilon, of course, these definitions coincide with the usual definitions without epsilon. Like epsilon transposition becomes just transposition of the matrix, and so on. Let me now come to the differential systems for master integrals. They, of course, we all know that they have a block triangular form because in particular, each sector corresponds to each sector. I mean, the integrals with a specific set of the denominators, they correspond to block, usually to irreducible block in these differential systems. Basically, this block corresponds to the differential equations for maximally cut integrals of this sector. Okay. Sometimes, although those blocks can be also splitted and block triangularized. I will talk about the blocks which cannot be block triangularized. So irreducible monodromy, for example, is irreducible. So now comes the main observation. The main observation is the following. Suppose that you have some homogeneous part of the system corresponding to some multi-loop integrals, to master integrals, and then consider the system which is epsilon conjugated. So we change the sign. M star means that it is transposed M with epsilon replaced by minus epsilon. So the observation I want to make is the following. It appears that those two systems are rationally equivalent. So there is a rational transformation which maps one to another. This is, to my understanding, quite non-trivial observation, and as we shall see, it results in quadratic constraints on the solution of the former equation. So, as I said, we can, if you are given some system, you can construct the epsilon conjugated system, and you can just check whether they are equivalent or not by using the algorithm that I presented to you earlier. So this is not a question of good luck. You can just construct, if they are equivalent in particular, you can construct the transformation matrix which maps one to another. I have to apologize because this observation is not new for the systems which are reducible to epsilon or to epsilon plus 1/2 form. Actually, this I already presented this on some conferences. Maybe some of you remember this. So to prove this, I mean, if the system is reducible to epsilon, to symmetric epsilon or epsilon plus 1/2 form, then you can prove the equivalence of the epsilon conjugated system in a straightforward way. For example, for epsilon, for symmetric epsilon form, we have this matrix is just the same as the original matrix, right? So we use here that S is independent of epsilon and that S transposed equals to S. So we have not only the equivalence of the systems, but they coincide with each other, just coincide. In epsilon symmetric form, the epsilon conjugated system just coincides with the original one. Okay, for epsilon plus 1/2 form, symmetric epsilon plus 1/2 form, it's only a little bit more complicated. So if you do the same thing, you see that this 1/2, it doesn't change sign under this star epsilon conjugation or epsilon transposition. Then you see that this is nothing but the matrix of epsilon of -1, so shifted epsilon. But as I said earlier, due to dimensional recurrence relations, those matrices which are shifted by epsilon, they are rationally equivalent, right? So we have, for both these cases, we have this property of being that epsilon conjugated system is rationally equivalent to the original one. The converse, we can also claim that if we have some system which is reducible either to epsilon or epsilon 1/2 form, then the statement that epsilon conjugated system is rationally equivalent to the original one is equivalent to that it is possible to find symmetric epsilon or epsilon 1/2 form. So for those systems which are reducible to these two forms, there is nothing new in my statement. But the point is that sometimes there are some systems which cannot be reduced neither to epsilon nor to epsilon plus 1/2 form. So for these systems, this statement is new. Before I show you these examples, the specific examples, let me make some simple but important remarks. First statement is that if you established the equivalence of the epsilon conjugated system for some for the expansion near some integer d0, then they are necessarily equivalent for the expansion near any integer d. K can be even and odd. So this may be non-trivial, but if you check the logic, you will see that this is basically the same thing which happens here. Like you can use this dimensional recurrences to claim that this matrix is equivalent to this one. Then here it is also in the same way you can prove that. So basically, this property of being the property that epsilon conjugation is conjugated system is equivalent to the original one, it holds simultaneously it holds simultaneously for any integer d, for the expansion near any integer d, or it doesn't hold at all. Okay. Another thing is that for this property to be possible, for this equivalence to be possible, it is obvious that the eigenvalues of the matrix residues should be either integer or half integer at epsilon equal to 0. We all, those who are involved in multi-loop calculations, they know that this is usually the case. Either the eigenvalues are integer plus some coefficients times epsilon, or half integer plus some coefficient times epsilon. This is compatible with the observation that I made. So this is, it looks like this is I mean, quite natural to expect that only half integers, only integer or half integer eigenvalues can appear. Okay, now what are the consequences of this symmetry? Well, if you consider the general solution in the form of path ordered exponent, then you will see that basically this property of equivalence, rational equivalence, it is translated to the following identity. So you have some relation between you have some quadratic relation for the matrices of general solutions for the equation original equation and the equation which is which has different sign of epsilon. So in terms of the solutions, you have the following. You have if you are given two solutions of the original equation, then you have to change the sign in one of them, and then you can claim that this combination is independent of x. So you can fix this constant by considering some asymptotics, but this is this relation is already non-trivial. Also, it is possible to fix the constant in each specific case, of course. So, but if we were interested in this exact solution in epsilon, then this would not be a strong statement, because here we have solutions of two different systems, which are different by changing epsilon with minus epsilon, by replacing epsilon with minus epsilon. But since we are interested in epsilon expansion of the solution, then we see that the expansion of those two basically the same up to alternating sign. So we have a lot of quadratic constraints for the epsilon expansion of the general or specific solution. This is what I want to say. Now, what are examples that we've already considered? First, massive sunrises for arbitrary masses. They are reducible to epsilon plus 1/2 form, and also they have this symmetry that I described. So we can write quadratic constraints for these massive sunrises, two-loop vertex. But those are examples that I show that I want to see. I mean, those on the right, the examples cannot be reduced to epsilon plus 1/2 form. So for those examples, it is not possible to construct this symmetric epsilon plus 1/2 form. They are also not reducible to epsilon form. So so this observation that I made, it is really new for those two examples that I have. In particular, for this very complicated example where we have 11 masters, you can check that this symmetry still exists. So there must be some quadratic constraints for this case also. And also for this example of forward box, let me just show you the simpler example for this forward box. It's there are 4 masters, so the differential system, the matrix in the differential system has the following form. It has quadratic denominator, irreducible quadratic polynomial in the denominator, and using the available algorithm, you can just construct the matrix which relates the original system and the epsilon conjugated system. So using this matrix, we can construct those quadratic constraints for the solutions which we yet don't know. So this is the problem, because since we don't know the class of solutions, we don't know the functions which which enter the solutions. We don't know whether those relations are known or not known yet for this specific example. But I think that they are at least quite non-trivial. Also, what I wanted, the last thing that I wanted to mention is that in principle, you can ask a question how to find the simplest form of the differential system such that this matrix which relates epsilon conjugated system to the original one had the simplest form. So this matrix under any transformation of functions, it also transforms in the following form, and then we don't know how to find the transformation in such a way that this new matrix becomes simpler. So basically, new algorithms are needed. But what we can say is that for epsilon reducible systems, it is possible to find to find the rational transformations such that then W becomes 1. This is made by passing to symmetric epsilon form. So if you pass to symmetric epsilon form, then this W becomes just 1. So you have the simplest possible W. A non-trivial thing that I've noticed is that it is also possible to make W very simple for those cases which are not reducible to epsilon and to epsilon plus 1/2 form, in particular for this specific example. Here, I don't know the algorithm. I just tried some ansatz, and I found that it is possible to make this W constant matrix, which is independent of both X and epsilon. So maybe there is something in this observation also. This is, I don't know, but as I said, it looks like we lack algorithms to answer to find this simplest form of this W so far. Maybe we will be able at some point to understand how to do this. Finally, I want to flash two examples, which are actually old ones, maybe at least this one. This example concerns two sunrise integral, and it is known that you can express the cut sunrise in terms of hypergeometric functions, and then the quadratic constraint is equivalent to the following relation, which I think quite interesting. At least if you ask Mathematica to simplify the left hand side, you cannot find it. It will not give you one. Although you can, once this relation is found, you can easily prove it by differentiation. If you differentiate with respect to y, you can easily get 0. Simplify the left hand side to 0, and then you have to substitute y with something simple, like with 1, for example. If you substitute y with 1, you will see that this relation is also valid for this specific point. So if the function, so basically this relation can be established in this way. So if you expand this relation in terms in epsilon, then you will see that you will have some relation for these funny looking functions. They are almost they are defined almost in the same way as we define polylogs, except that the last weight is now defined by this binomial or trinomial probably coefficient, while for polylogs we would have here something like inverse power of j or j plus 1, something like this. So the only the slight modification of the definition, and this is the function in terms of which those hypergeometric functions are expanded, and now we have this quadratic constraint leads to the infinite set of the relations for those functions. For any n, the following constraint holds. For n equal to 0, this is probably can be reduced to Legendre relation for complete elliptic integrals. Also, I have the relation for L-loop sunrise integrals. So it is convenient to introduce the following functions, the following integrals in coordinate space. They naturally appear in the definitions of sunrise integrals. You have some Bessel E functions, I functions, and K functions, and so you can just see what the definition is. Then we have a lot of constraints for those functions which I define, in particular this one, and also you can put m to some specific value. In particular here it is 3 loop case, and m is put to pseudo threshold, to specific pseudo threshold, and then we have such a nice relation. Many others many other relations can be obtained. In particular, Broadhurst and Robert some time ago conjectured remarkable quadratic relations for the specific integrals, for the integrals of this kind, for specific set of these groups of indices. Here D and B are rational numeric matrices. Recently, these relations have been proved in this paper with a except that matrix D was defined differently, but one could check that for specific n, this definition gives the same result as the original definition by Broadhurst and Roberts. So my statement here is that using the quadratic relations, it is also possible to do the same, basically, with yet another definition of D, but we could reproduce this the right-hand side of this equation. This is all. My summary is that there is a hidden, there seems to be a hidden symmetry in differential equations for multi-loop integrals, and this symmetry results in non-trivial quadratic constraints for the coefficients of epsilon expansion. Also, there is a natural question of how to find the form where this constraint is the simplest, and unfortunately, we don't have algorithm to find this simplest form, to find the transformation to this simplest form. So probably we have to invent some new algorithm. Thank you.
Great, thanks. Let's, I'm gonna give people a couple seconds to unmute themselves so we can all applaud for Roman. All right, and we already have a question from David.
Thank you for this lovely talk. I have a remark about the recent and very impressive work by Javier and his co-authors. They've not quite proved what David Roberts and I did, because we gave an explicit construction of the Betti matrices, which are very simple. They just involve Bernoulli numbers, and a highly refined formula for all loops for the de Rham matrices. And all that's happened at present is that they have a way of constructing up to a finite number of loops, the de Rham matrices, and observing that they are equivalent to ours. But they have not yet proved our all loop formula. I wonder if your de Rham matrices are more amenable to proving our all loop formula.
Yes, it is quite explicit formula. It has the form of product of many matrices. The number of factors depends on n. Yes. So this is explicit formula, yes, but for any n. But it has the form of the product of, roughly speaking, n matrices, okay? So, but otherwise it is quite explicit.
Mm-hmm. And just one more question, if I may, about even and odd dimensions. I was very interested in your epsilon and epsilon plus a half. Now, we know that for massless diagrams, even dimensions are easier than odd ones, right? But conversely, for massive diagrams, odd dimensions are easier than even ones, because the Fourier transform of a 1 upon p squared minus m squared in a odd number of dimensions is an elementary function. So have you actually played your games for massive diagrams near 3 dimensions?
We did it for sunrise diagrams. For those, it is possible to the epsilon expansion near odd dimensions. It is it has polylogarithmic coefficients.
Yes.
And also you can even introduce analytic regularization, so to say. So you have to you can also add some small powers to the propagators, and still the expansion with respect to analytic regularization parameters will also be polylogarithmic.
So I recommend this to mathematicians. As physicists, we like to live near an even number of dimensions, 4 being more preferable to 10. But mathematically, I think people would be well advised to look at massive diagrams near odd dimensions. Thank you.
All right, we've got a question from Claude, who can't raise his hand because he's a co-host.
Yeah, so thanks, Roman, for the nice talk. I was just wondering, so you presented your quadratic relations. Did you ever check if there's any relationship to what is called the twisted Riemann bilinear relations? Because what you show and what you obtain should be actually part of that general theory. So these quadratic relations should be what mathematicians call twisted Riemann bilinear relations. And then the question would be, is there anything you can learn either from knowing what it is in math, something we can learn, or maybe something we can teach mathematicians explicitly about what these relations are?
Well, we didn't check it yet, but we do believe that they are the same. For example, for the Lauricella FC function, which appears in, as a solution of the differential equation for massive sunrises and tadpoles, watermelon type tadpoles. So yes, it looks like they have a close relation to this. But the point is that you see, for example, at least as far as I understand the paper by Xavier Frisson and others, they used a heavy machinery of homology theory. But in our approach, the relations appear as they're trivial. I mean, you don't have to do something very difficult to derive them. You just see that the symmetry of the differential equation, you construct the quadratic relations, and that's all. So in a sense, I hope that this approach that I presented here will be helpful even for the complicated cases where, I mean, it would be easier than to do something more involved using twisted Deram homology or whatever.
But it may also be worth comparing it to what Sebastian Misera and Pierpaolo Mastroli are doing, because they also have a way of getting the twisted relations from, well, a Feynman diagram dimensional localization setting. So that may be another way to approach this.
Yeah, I agree. Yeah. But it's usually those examples are not. I mean, you cannot restrict yourself with one loop, right? So in one loop, you don't have such problems. It's all examples.
No. But if you look at their papers, they derive them for two-loop elliptic integrals. So
yeah, my point is that it takes time to compare also.
Sure.
Okay, we've got a question from Lorenzo.
Yes. Hi, Roman. Thank
Hi.
you for the, maybe you see me. Yeah. Thank you for the talk. So I have a question that is, I don't know exactly what it is, between a question and a comment. So you're talking a lot about this epsilon plus 1/2 form, and now also this new integrals that are you cannot put in this form, right? And then you talk about what is the simplest way to go from one representation to another. Now, my question or my comment, I don't know, it's that, so my understanding in the polylogarithmic case, there are multiple epsilon forms, right? In a sense that epsilon form is not enough to say that you are canonical. You need to have also the matrix in a special form. You need to have D-log forms, right? And the fact that the matrix is in that particular form somehow can be understood from studying residues of the integrand. So I was wondering if you see, or if you have tried to connect this epsilon plus 1/2 form, or even more complicated cases, or different types of epsilon plus 1/2 form, different types of matrices with particular choices of integrands, right, for the Feynman integrals. If you have ever seen a connection of this type similar to the ones that happens for polylogs.
Yeah, I see. Well, I would say so that I'm always trying to be satisfied with differential equations only. Okay, So I want to see everything from the differential equations. I believe that this can be promoted to, so to say, to automatic approach, like, right? So if you consider integrand, then of course this is great, but still you are probably obliged in most cases to, I mean, to consider one by one example. So you cannot do it automatically, basically. So this is more laborious, and I would like to have some, so to say, industrial method when we can do everything on the machine. And so, frankly speaking, I didn't think in this way. I mean, I didn't.
Yeah, no, I understand your point of view. Sorry, I was just wondering. I was just asking because I think you can learn something also from the other approach. Maybe at some point one needs to look at both. I mean, it's true. It would be nice to be able to do everything from the differential equations. Yeah, but it's.
Yes, I agree. But you see, what you said about different epsilon forms, that I didn't understand, because to my understanding, epsilon form is almost unique. I mean, you can do some constant transformations, but up to this is all.
Well, I guess I could do something very perverse where I integrate out the homogeneous part, or even not just the homogeneous part. I integrate out pieces of the differential equations, and in the matrix, I mean, I get an epsilon factorized, but in the matrix, I get something. Maybe I could get logs even, couldn't I?
That I know.
Inside the matrix, right?
Okay.
I mean, and this would be this is an epsilon. This is an epsilon form, right? But it's not what you want. So from the point of view of polylogs, we know what we want. To me, it's not clear that in the case of non-polylogs, we even know what we want. And that's why I thought that going from the residue part of the integrands, where you, in a sense, know what you want, maybe, but it's not that clear either, you can, make a connection and try to know at least what you're aiming for. So to me, it's not clear that I know what I would be aiming for, for inside the matrix.
Yeah, I see, yes. But for epsilon form, still, you don't want logarithms, right? You don't want transformations which are not rational. If you can go with rational transformations, then that's what you want.
Of course. Okay. Thank you.
And then we've got one more question from Rob.
Hi, Roman. Thank you very much for the nice talk. I just wanted to ask you, would you be more successful to make these transformations if you allowed for algebraic transformations? So, I mean, is it a proof that you can't put these two examples in epsilon form or epsilon plus 1/2 form, or is it just that you fail with rational transformations?
Well, you see, it depends on what you call algebraic transformations. Usually people call, I mean, this is what I was saying here. It's it's something here, right? So usually you want to make some change of variable. The old variable is a rational function of the new one. Then you can consider transformations which are rational in terms of new variable, and these are not necessarily rational in terms of the old one. But then I can tell you that this is definitely not possible. I mean, the criterion that we devised with Andrei Pomeransky, it tells you that, I mean, it can tell you that it's not, even if you do this change of variable, it's not possible to find epsilon form.
No, but that's not what I'm talking about, Roman. I'm talking about things which are intrinsically algebraic, things which cannot be rationalized. So, for example, our recent work on the mixed QCD Leibniz-Dralian integrals, the planar double box for Baba scattering with, same mass here and here, this kind of thing. So, I mean, there's for sure examples where you need to have square root factors, which are provably not rationalizable through any locally invertible variable transformation, right?
So you mean you have some relation between old variable and the new one in terms of the some polynomial of both equals to 0, something like this, or what?
No, what I'm saying is, what if you have a leading singularity which is intrinsically algebraic? Does it make sense what I'm asking? Or?
Well, you see, if you express y in terms of x, even here you will have square roots, okay? At least. I mean, I do allow for these transformations. I mean, I don't allow those ones where you have both ways. Like you cannot express x in terms of y rationally, and you cannot express y in terms of x rationally, okay? Those are transformations, I mean, which we don't know about. I mean, I don't know how to prove that such transformations do not exist for each specific case.
So, I mean, I guess the reason I'm asking is just that I find your epsilon or epsilon plus 1/2 idea very attractive. And I was wondering if maybe with luck, this is even something universal, but perhaps one has to allow for more general transformations to arrive at this form. Do you think that's conceivable, or is it just fantasy?
It's quite exciting, I would say, but I don't know if it's possible.
I have one further question, but my son is banging down my door, so maybe I should just email you. Thank you, Roman.
And then we actually have one more quick comment from Claude, I guess.
Yeah, so maybe, Roman, I want to pick up on what Robert was asked, which I think is a very important point. So what Robert was asking is, imagine you have something, let's do it let's do it backwards. Imagine you find a D-log form, an epsilon form with D-logs that contains square roots which you cannot rationalize. And so there are these P's, they exist. So there are situations where there is an epsilon form, but you cannot find what is you call F on your transparency.
Yeah.
So what can you say about those cases?
I do understand now. You mean this situation probably, because
no, not even this. I mean, I'm saying there's no F and no G. It just doesn't exist. You cannot find any change of variable, even if you split it up in different pieces, such that it works.
Yes, that's what I mean. But I mean, here I said that okay, you have two variables y and z. It is I do know examples where you can find epsilon form, but at the expense of using both y and z in one and the same matrix. And this is I mean, it will be matrix which is rational in both y and z, and still there will be no one variable change which rationalizes it. Okay.
Okay, yeah, let's call it like this. But it means that essentially there's no way to rationalize it, right?
I agree. Yes. Sometimes it happens. I know one example actually.
Well, there are many, and in particular the ones that Robert mentioned.
Oh, I know two. Excuse me. I know two.
Okay, I know three.
Okay, let's go ahead and thank Roman again virtually. And then we now have a break for about 20 minutes. We'll reconvene at 1/4 to get a couple more talks. But please feel free to stay in the room and chat with people. Unmute yourself. We'll check some slides for the next speakers in the background, but go ahead.
Okay, thanks. So I'd like to thank the organizers again and for giving the opportunity to present this work. Though my title suggests I'll be talking about how to compute the phase space integrals, but I also give the phenomenological motivation behind this. So basically, how to compute the QCD electric correction to Z-Boson production. And this work has been done in collaboration with Roberto, Federico, Ilario, and Alessandro. And we study all the integrals, including virtual loop integrals and also the phase space integrals, which are required for NNLO mixed QCD electric correction for Z-Boson production, which is basically a part of full Drellian contribution. And you don't basically need why we want to compute the Drellian correction to such precise order. I mean, this is one of the standard candle process for detector calibration, and there are so many physics motivation behind it. So to name basically the three of them is that detector calibration and then precise measurement of various electric parameters, for example, W Boson mass and sin square theta. Additionally, many BSM physics, they mimic the same final state. And so there is a possibility to find BSM physics behind this same final state. So we need precise prediction for Drellian. This has already motivated us for quite a long, and we have quite a good predictions, mainly from the QCD side for Drellian. And recently there has been works by Dulert and Mistelberger to obtain the full NQLO QCD corrections, which takes us to the most precise limit. Now, when we are going so much advanced in QCD side, whether we need the NNLO QCD cross electric correction or not. So, and additionally, that hadron colliders are aiming for per mil precision, and QCD corrections at NQL also gives us almost per mil precision, and to match that accuracy, so whatever we can get, so which any higher order corrections which gives us per mil precision we should include. And inclusion of such higher order contributions also reduce the uncertainties which comes from unphysical scales, namely renormalization and factorization scales. Hence, the higher order corrections are very much important. So if we just look at from naive argument of coupling strength, that is comparing alpha s cube with alpha s alpha, we see that they are almost same. And so we expect similar contribution just from this naive argument. However, in some phase space points, fixed order electric corrections can become very, very important because they contribute through the large logarithmic enhancement, which can be weak logs, also the QED logs, both are Sudakov types. And we need to know them exactly so that they can be resummed. And these resummed predictions actually helps us to have a better prediction or more precise prediction. Next point comes when we see that for the W mass measurements, the NLO electroic effects are quite large. And we also know that almost any NLO QCD corrections are large. So this mixed QCD cross electroic will be the NLO QCD on top of NLO electroic. So if we aim for less than 10 MeV precision for W mass, this is a must needed. Additionally, the appearance of photon-induced processes, that means we have new type of process, we have photon in the PDFs, which opens a new channel. So all these physics motivations are quite important and really motivating to compute this process. So to summarize that if we want to achieve less than 10 MeV precision for MW, which is the most important part, we need the lepton distribution at per mil level, and that implies this process needs to be computed. And then I have another slide on a different note. I mean, we know that when we compute Drellian, we use the experimentally measured values, for example, Fermi constant, W mass, or Z mass as input. And this input choice, we have a general choice for G-mu scheme where we consider the Fermi constants MW and MZ. However, for theoretically speaking, we can also consider alpha and MW MZ as our input. So what does it differ then? The difference is that there is a relation between G-mu and alpha, which gets corrections from one loop electroic and then so on, mixed QCD electroic corrections and so on through delta R. And when we are computing pure QCD corrections, that means we are neglecting the contributions from delta R. And so this is leading order in electroic. And from this relation, we can compute alpha through the values of G-mu and sin theta and MZ, which are experimentally measured. And this alpha value, which is denoted by alpha G-mu, and the experimentally measured alpha value, which is denoted by alpha 0, they differs by 3.53% at leading order in electroweak, I mean at leading order of this equation. And that is quite important because using these two schemes, because of this, we have a difference in our leading order result or NLO QCD result or any NLO or any QCD correction we do thereafter. And the difference remains 3.53%. And we can see that if we have electroweak corrections, just electroweak corrections on top of leading order, the difference comes down to 0.53. So that means we need to incorporate electroweak corrections. And then you say, okay, we are fine with NLO electroweak, then we include all the QCD corrections. Now that's not good because then we have the QCD corrections, for example, delta 1, 0, which is NLO QCD. And then there is nothing to suppress the contributions coming from delta 1, 0, which is making a difference for G mu and alpha 0, and the difference increases to 0.89. So that clearly implies that we also need the mixed NNLO QCD cross electroweak corrections. And I hope that's quite well motivating. So after that, let us fix the notation, which you all know, that we have the total cross section, which has to be convoluted with the with the PDFs, with the finite PDFs convoluted with the finite partonic cross sections, and they are expanded. The finite partonic cross section sigma ij is expanded into to alpha and alpha s, and we compute sigma 1 1, and that's for the notation. So then I come to what are the contributions and how we compute them. So purely at two-loop level, there will be mainly three types of contribution. So one is virtual. So there will be virtual two-loop diagrams where there will be one or two massive bosons or massless, including photon, and one gluon. So these kind of diagrams will contribute. Then there will be one loop diagrams with one emission of real particle, and there will be double real emission. So with these three kind of contribution, that they will be there in pure NNLO level, and there will be additionally contributions from one loop. The loop integrals we have to integrate, and finally we will see that we find the result in terms of constants because we are considering the on-cell Z boson production. So the constants will be multiple zeta values and cyclotonic constants, and the phase space integrals we have to integrate the momenta of the real emitted particles. They are often performed numerically, but we are trying to obtain the inclusive production cross section. So we require an analytic expression. And finally, when we are done, we will see that these contain standard HPLs with different letters and also elliptic polylogs. So here now, for our convenience of the calculation, we divide the whole process in basically 4 types, considering the different vector bosons. So one is when there is photon, that is simpler, and that we don't talk about hereafter. Then there can be a single Z propagator in the loop. Note that we don't include any Z boson or any massive boson in the emission. So whenever we have emission, it's either a gluon emission or a photon emission or 2 quark emission, because emission of massive boson is infrared finite, so can be treated as a separate process. And then there is the division EW1 when we consider only single Z propagator, EW2 when we have single W propagator, EW3 when we have this WWZ vertex. And note that we can treat them separately, which is better for us, easy for us, convenient for us. And QCD QED is gauge invariant and finite. EW1 is separately gauge invariant and finite. But when we compute EW2 and EW3, we have to compute them together because together they're gauge invariant and finite. So, and the generic procedure is quite well known. You draw the diagrams using Q-graph. So, and then use the form routines for several different algebraic manipulations, or the low range Dirac and color algebra. if we have the, when we have the phase space integrals, that means we have a delta function. We use the reverse unitarity technique to write down all the deltas in terms of propagators with I epsilon prescription. And the advantage of doing this is that now we can use all the techniques for develop for loop integrals. So for example, when we go next, that decomposition of the dot products to obtain the scalar integrals, and then we use the IPP relations. Once we use the IPP relations and we find the master integrals, and finally we solve the master integrals using differential equation, and that is the generic procedure to obtain all of them. So let us see how we do them. So before that, I make few comments. So first comment is on the method of differential equation. We do not use canonical form for the system of differential equations. So when we are not using canonical form, we are expected to find coupled differential equation, which most of the cases it's maximum 2×2 or 3×3 matrices, which we decouple them. For 2×2 it is easy, but for 3×3 we use one of the following uncoupling algorithms to make the decoupling easier. So either Zurcher or incomplete Zurcher or Abrahamov-Zima. And on the dependence on MW and MZ. So for example, if I go back this kind of diagram, then we have WWZ vertex, and or even this kind of diagrams where we have a W inside and a Z production. In that case, we have two scales, which is difficult to handle at the moment. So what we do, we expand all the propagators, basically the integrand containing MW around MZ with delta M square. So once we do the expansion, and we can treat all the integrals as a single mass integral. So basically it boils down to single scale problems, which is much easier. And through the expansion, we can get a nice phenomenological result. So whenever we have two mass, we do the expansion of MW around MZ. And I introduce more notations. So we have the variable Z defined as M square over Q square. And at various points, we need to do variable transformations to T, rho, or W, you will see. And after doing all this transformation, we only have few letters. These are the letters that appear in whole the process. And among them, they are the third and sixth and fourth root of unity. So with everything defined, let us go to the computational details for starting from the double virtual. So for the double virtual case, we have two different kind of topologies. So one is when we have a single massive line inside, everything is massless. And another case when we have two massive lines inside. So for the first case, we define the variable x. And for the second case, we define the Landau variable XL. Now, to take the help of differential equations, we compute the integrals considering offset z, so that we can use differential equation. And the boundary conditions are easily obtained for x equals to 1 and x else equals to 1. And the result can be written in terms of HPLs with alphabet -1, 0, 1, and 6, 0, and 6, 1 only. So this can be obtained for the offset z. Now the trick is, or the main part is to take the Onsel limit to achieve the Onsel result. So for EW1, this is simple because we have MZ inside and we have the Z production here Onsel Z. So the limit is basically x to -1, which is simple. For EW2, we have two cases. We have in case of x, so when you have a single W propagator, we have to do the series expansion corresponding to limit Q square going to MZ square for x. And for this case, we also cannot take the limit XL going to this. Rather, we have to do a series expansion around delta M square, because at the end, we want a precise result and we have to do the series expansion of MW around MZ. So once we perform the series expansion, we have HPLs with arguments what we saw earlier, -1, 0, 1, 6, 0, and 6, 1, but sorry, with the letters that we saw earlier, but with argument R2. And that's a little bit of problem because if we have HPLs which are dependent to each other, we will not see in the final stage the analytic cancellation of the poles, which is very important for us for inclusive production. So we have to reduce all the HPLs to a basis. So we chose the basis introduced by Hen and Smirnov. So finally, we write down all the HPLs with -1 in the argument and with R2 in the argument, and with all the letters -1, 0, 1 and 6, 0, 6, 1 to the basis chosen by Hen and Smirnov. And this reduction of the basis is very much important for analytic cancellation of singularities. So next we go to the computation of real virtual. So for the real virtual case, we have different kind of topologies when we have QQ initiated states or work clone initiated states. But the general procedure is quite same. Use the reverse unitarity, get the IBP reduction rules, get the master integrals, differentiate and solve the differential equation. Excuse me, can you see my cursor?
Yes, we can see it.
Okay, sorry, and there is a glitch. But now the problem is that we have few square roots. Well, you say that, okay, we go ahead with these square roots and we define our iterated integrals, which is fine. But as we know that the numerical evaluation of the iterated integrals with square roots is not efficient. So we need to rationalize them. And as Roman was saying in the earlier talk, sometimes it is better to use different rationalization rule and make subsystems so that we have more than one argument or one variable. So, and the advantage of doing that is that we have good letters, and in the end we need a first numerical evaluation. So if we have good letters, that is much better. So that's what we do. We divide this system into pieces, and so for example, we take 1, -1 and 0 with the cyclotomic ones, that's the system, and then 1, -1, 0 with these square roots, that's another system, and 1, -1, 0 with this one, that's another system. And then each system gives us different arguments using the transformations to Z, rho, and W. So once doing that, I repeat that we have our result in terms of HPLs with only these letters, which helps us in very first numerical evaluation. Let's take an example. For example, we have simple integrals J1 and J2, where J1, the solution of J1 involves a square root letter, and the homogeneous solution of J2 contains standard kernel, but it depends through the non-homogeneity to J1. So first what we do, we try to avoid the square root letters or coming to the single pole of the whole matrix element. So because I mean, we know that our single pole is have a simpler structure in HPL. So whatever square roots are coming, or the other square root later converted to different arguments, they are coming to single pole, they will be cancelled eventually. So we try that beforehand. So we try to find a combination of integrals J0 such that combination of integrals J0 in terms of J1 and J2 such that we can solve J0 for the poles at least with simpler HPLs. So the combination becomes, the differential equation of J0 becomes like this, where the non-homogeneity depends on J1, which is proportional to epsilon. And then of course, I mean, if we have a square root letter in J1, say at 1 over epsilon, we lose it at J0 minus 1 at the poles, but we of course have it at J0, 0, that is the finite piece of J0. So this way we avoid all the square roots or we move all the square roots or the bad looking HPLs to the finite piece. So, and our poles, the single pole of the whole matrix elements remain clean, and hence allowing us for a nice cancellation. Now the next, when we solve J0 for the finite piece, which of course have the square root pieces, we perform the variable transformation as we discussed earlier. So we divide the non-homogeneous piece in two different pieces, one depending on the variable z, another depending on the variable w, which comes from the rational transformation of the square roots, and then we treat them separately, and finally we have our results. So the results looks like this, and notice that we have j1 minus 1, which is depending on w, and we don't need to compute j1 0 because of our useful combination. For j0 0, that is again for j0 minus 1, the answer is simply in terms of HPLs with z, which is simple. And for j0 0, now we have the answer in terms of the mixed variable. We could have written everything in terms of w, but in that case we will lose, for example, these pieces. These pieces will be translated to variable w. Now the bad thing about losing these pieces is that there is a singularity at half, but this is not there in our matrix elements. This is pseudo singularity, and obviously there will be other terms from other integrals. So there will be same term from other integrals which will eventually cancel all these singularities, and we want to get it done analytically. So that's why this division of variables is quite important, because then in the end we have the finite answer which doesn't have any spurious singularities or pseudo singularities. So that's how that's why we make these little tricks. So when we compute the real virtual integrals, we also need to compute the boundary conditions for that. So the generic idea is quite simple. Compute the exact solution of the one loop integral which contains the massive lines, and then take the soft limit. Once we take the soft limit for the exact solution, we can compute the two body phase space integral. This has been known. But for the massive boxes, we take a different approach. So for the massive boxes, first we assume a general structure for the massive boxes in terms of T and U. So when we take the soft limit of any one loop integral, what we generally look for is the structure of T to the power n epsilon. So these kind of structures, they actually contribute to the phase space integral, or to the soft limit of the phase space integral. So when so we assume such a structure by looking at the massive box, but the coefficients obviously is unknown. Now with the massive box, there can be two real virtual integrals. So one is called 6den, and other is with 7den. How we define them? So the T propagator in the bond, so if we go to the graphs, so there is this T propagator in the bond connection, and without or with this one. So without this one is called 6den, and with this one is called 7den. And so we define them, and we can obtain the soft limit of the 6den integral using IBP reduction rules. We can also obtain the soft limit of the 6den integral using our assumed structure, and then we compare two to get the unknown coefficients, and then we are done. And then we take the known coefficients now to compute the 7den integrals. So this is much comparatively easier to compute than computing the hypergeometric function and taking the soft limit. Okay, now I come to the computation of the double real. So again, the same process, reverse similarity, IBP, and I don't repeat. And here we have another different set of kernels. Similar to real virtual, we write the system in a separate dependent variable, in a dependent variables, and separately treat them. As a result, we have some new letters here, but the calculation is almost similar to real virtual. However, when we treat the double real, we face a subsystem which is elliptic, a 3×3 subsystem, which is not first order factorizable, giving a set of three elliptic integrals I1, I2, I3. And as you can recognize immediately, the homogeneous part of this one for the virtual case was studied by Aglietti, Bonciani, Grassi, and Remedi to obtain the results in terms of elliptic integrals of the first kind. And recently by Brodel, Dulert, Penante, and Tancredi to obtain the result in terms of EMPLs. So in our case also, in each order of epsilon expansion, the 3x3 system reduces to 2x2 and 1x1 subsystems, and they can be solved with standard HPLs for the poles. So when we have I1, I2, I3, actually I1 and I2 doesn't have pole in our definition, and I3 has one single pole, which is simple HPL. And then the finite pieces have elliptic polylogs. However, there is a problem because the IBP reduction introduces a 1 over epsilon in the coefficient of these integrals. So that means we need to compute it up to higher order in order epsilon. But the main problem is that the finite part of the integrals which contain elliptic polylogs, they contribute to the single pole of the whole matrix element. So we can easily expect that this contribution, these three contributions coming from three integrals, they should conspire, and this should conspire to some simple HPL, because all the other integrals contribute to single pole of the matrix element. They are simple HPLs. And finally, we need cancellations. So we've tried to find a combination of the elliptic masters, and we find I0 as a combination of I1, I2, and I3. And the differential equation order by order for I0 is ordinary for at least the pole and the finite piece. So we can solve it and get the result in terms of HPLs. So we are done in some part, because using I0, we can solve the poles, we can get the cancellation of the single pole, and now we have to compute for the rest to obtain the finite part. But we get the analytic cancellation of the poles. That's the first step. Of course, when we try to compute the finite part of I0, they cannot, this cannot remain independent of I2 and I3. I mean, this has to appear somewhere. And so they contribute to EMPLs with finite part of the matrix element. Now, to avoid the numerical evaluation of the EMPLs, we expand in logarithmic series. So we perform series expansion for I2 and I3 around z equal to 1, half, and 0. And we impose the initial conditions in z equal to 1 and match the different series in intermediate points. Now for I0 to compute, we again take the procedure as discussed in real virtual case. So we compute part of I0 as exact form, which is basically is dependent part, which depends on HPLs in closed form, and the rest, which depends on I2 and I3 or EMPLs, we compute them in expansion. So why do we do that? Because we see that these are the expansion results. So I1 in blue, this is I2, and this is I3, and the expansion results are quite nice, or they're quite nice. And for the expansion result of I0, which the part which is expanded, that is also quite nice. So for numerical evaluation, they're quite helpful. And the exact closed form of I0, that contains some HPLs, which contains all the logs and divergences. So they also cancel with other pieces, so that for the rest of the result, which is closed form, we also have a nice numerical evaluation. So with that, now I also need to compute the boundary values for the double real, which is taking basically the soft limit to z to 1. For that, we scale the momenta, the outgoing momenta L1 and L2 with 1 minus z. And eventually, when we do that, all the scalar products will be scaled as 1 minus 2, 1 minus z, or 1 minus z square. This is basically the prescription which was taken for NNLO hex calculation. Now, for Z boson production, all the momenta, all the propagators which appear with the mass can be easily parameterized. Using this parameterization can be shown that they do not contribute to the soft limit. So we can easily compute all the sublimits of the integrals containing the massive lines through the ones without the massive lines. So once we compute all the such double real, real virtual, and double virtual integrals, we use them in our matrix elements and obtain the result, the unnormalized result. Now we need to renormalize them. The renormalization of electroic sector is quite involved. Now for us, there is no alpha s renormalization. The quark wave function need to be renormalized, and we use the Onsen scheme. For the rest, for the neutral current vertex and everything, we use background field gauge, with the advantage that the vertex and the propagator contributions are separately UV finite, so we compute them separately. Once we find the UV result, we obtain the finite Patternic cross section, which now needs to be convoluted with the physical pattern densities. We have two parallel photon codes to obtain our numerical result. In one code, we use harmonic sums and GNAP to evaluate all the sigma ij separately, and we save them in grids, and then use interpolation routine. This is quite fast because of our compact structure. We can evaluate each sigma ij in few minutes for quite a good precision. And we also use in another program, we also use handy G at the during the integration to evaluate sigma ij. And finally, we obtain our results. So before presenting the final result, I want to show you the specific sigma ij because of some interesting point. So one interesting point to note is that the behavior of the contribution from AW1, that is the Z, is almost similar to the NNLO QCD. That's bit expected because we can almost say like this is factorized. This can be the structure we look at coming from the soft gluon, and for both cases, for QCD, NNLO QCD and EW1, when there is a single Z boson, the function appearance of the functions are same. So we see a similar pattern in both cases. Another interesting point, we note that in the inset, if you find that there is a kink at Z equal to 1/4, and that is expected also because that suggests the diversion production threshold. So there will be one diagram when with the Z particularly that UU bar going to Z and decaying to UU bar again. And we can have a cut at that Z and the ons of Z. So indicating that this is the diversion production threshold, and that we can see in particular matrix elements. So finally, I'll come to my results. We have the NNLO QCD result pointed here, and finally, when we have the total cross sections added, we see what we looked for, that the difference between these two schemes really the spread reduced to 0.23%. So that is the effect of including the mixed NNLO QCD cross electric corrections. And obviously the total correction is again as expected. This is almost per mil level to the bond. The NNLO QCD QED correction is like 0.03% of the bond, while this mixed one is larger than the QCD QED by almost a factor of 3, and thus gives us a per mil correction, which is quite important. So I'll come to my summary. We computed the full mixed NNLO QCD electric contribution to Z boson production, which is an important ingredient to the full Drellian. We use all the methods of loop computation for phase space integrals. We have computed the two loop virtual and phase space integrals with massive lines, and the solutions are obtained mostly in terms of HPLs and several constants and multiple zeta values and cyclotomic HPLs at 1. The contribution from elliptic polylogs are obtained as series expansion. Then we have performed cross checks analytically and also numerically with the available QCD-QD result. There has been also recent computation by Monte Carlo, and we also agree to expected numerical accuracy to that result. And few remarks that the computation of the master integrals for virtual and phase-space integrals is challenging, and it is only possible due to current development in loop computation. Understanding the polylogarithms in detail really help in such calculation. For example, when we saw for the double virtual case, when we are trying to reduce the polylogarithm constant to a basis, it was very much necessary to achieve the analytic cancellation of the divergences. Also, in between, in case of real virtual and double real cases, there are such cases which also appear. And for them, to see the analytic cancellation, this is quite important. Understanding and the manipulation of polylogarithmic functions, transformation of variables in great detail also helps us to achieve a compact solution. And because of this, now we can easily evaluate the numerical solution, or we can easily get the number in few minutes because of the compact answer. So I still have some more time, so thank you for your attention.
Okay, thank you very much. I suggest that we take 2 or 3 seconds to unmute everybody. And then we give Narayan a round of applause. Okay, so we still have a bit of time, so we have time for questions. I see there's a first question by David. David, please go ahead.
So congratulations on this very sustained piece of analysis. It's very impressive. Would you go back to slide 11, please? So with deference to the barking dog, I have a historical remark to make about the appearance of the golden mean in your calculation. We had a very nice remark by Roman going back to 1934. The first example of multiple polylogarithms of the golden ratio, square root of 5 minus 1 upon 2, date back 280 years to John Landon.
Okay.
And when I was dealing with polylogarithms of the sixth root of unity, which you have everywhere in your equations, Deligne suggested that there were no conjectures for fifth roots of unity. But what I was able to find is that if you go to the real subalgebra of fifth roots of unity, which is the golden mean, then there's a beautiful mathematical structure. And I'm absolutely delighted to see 280 years later that occurring in practical calculation and high geophysics. It points to the unity of mathematics. And I have an article on the archive entitled Multiple Landon Values, where you can find more about John Landon's remarkable work.
Thank you. Thanks for the information.
Okay. More questions for Narayan? So maybe I can ask a question. So Narayan, so you commented at the beginning on the NNLO, and then you said that your calculation is in some sense complementary because you include QED radiation, and there's also the question about the scheme you necessarily use for the electrodecoupling. And now imagine I wanted to get the best prediction that is on the market. I would want to compute our NNLO calculation with your mixed QCD electroweak. What would I need to do? Because I'm wondering in specific, well, one thing is the scheme that is used for the randomization, but in particular the PDFs, because what we usually do is we use PDFs that are inclusive in QED.
Yes.
So what would we need to do to combine them?
I did not make comment on this because it will be too much probably, but I mean, when we use, for example, pure QCD PDFs and then QCD, Lux QED PDFs, there is a hell lot of difference. So, I mean, when we use, for example, NNPDF QCD and NNPDF QCD QED, and that difference is also quite large. So when we, I mean, the contributions from photons, they are there. So when we are including the QCD QED and QCD electroweak corrections, we should consider them in the PDFs. And also the contribution, I mean, there is no radiation for W. So there is no contribution for the W PDF. But to the element, I mean, I think there can be contribution from the electroweak sector also. So the PDFs also can change a bit, including this electric correction. So if we finally, if we want a precise result when we are including EOR and QVELO and NNLO QCD electroweak, I mean, my thinking is that we can take mixed PDF, because when we take mixed result, we have to take mixed PDF. So QCD QED PDFs.
What do you mean by mixed? You mean take Lux QED?
Lux QED, yes, yes.
So,
Lux
and that
QED.
would be sufficient, but are they known? So at which order in QCD are they known? Are they known at NNLO in QCD, or are they only known?
They are known up to NNLO QCD QED. So,
okay.
So they have incorporated all the photon correction in the PDF.
Also at NNLO, even.
Also at NNLO.
Okay. Okay. Thank you.
Okay.
More questions? Okay. I do not see any further questions, so we can all thank Narayan.
Thank you.
And then we can move on to the next talk. Okay, so our next talk is by Federico Zerbini, who's going to give us an overview of elliptic polylogarithms and superstring amplitudes.
Okay, hello. Can you see me? Can you hear me?
Yes, we can see the slides and we can hear you.
Okay, great. So thanks a lot for inviting me to speak to this conference. It's really the third Elliptics conference that I'm attending, so I think I know a lot of people out there, and so hi to everyone I know. And so I was asked to give a review talk on some mathematical aspects of superstring amplitudes, in particular beyond genus 0. And this is not so easy because there are a lot of things to say. So I've decided to focus on elliptic polylogarithms and to give a mathematical introduction to some aspects of elliptic polylogarithms, which I believe are the right aspects to look at if you want to generalize all this to higher genus. And in the very last slide, maybe I will comment a little bit about how one could think of going beyond elliptic polylogarithms from the mathematical viewpoint. Okay, so let me start. So this is the plan of the talk. I'm planning of spending maybe 10 minutes on the classical polylogarithms and the genus 0 amplitudes, because this will motivate the rest of the talk. Yeah. And then I will go to some, let's say, hardcore mathematical concept that I will try to make as easy and accessible as I can in order to justify how people define elliptic polylogarithms. And then I will mention what's the state of the art, or some highlights on the state of the art in genus 1 amplitudes, and what's to do and what's not to do in genus 1 and beyond. Good. So let's start with genus 0. Everyone knows about multiple polylogarithms, I guess. They are sometimes presented as Goncharov polylogarithms when they are presented with this definition. So I wanted to be quite precise here, so let me mention a couple of things. So we have a formal alphabet with 2 letters, and we form words in non-commutative letters. And then I want to cut out of the complex plane 2 lines, which are the branch cuts, which you can pick, for instance, going straight from 0 to I infinity and from 1 to I infinity, so that the logarithm function is well defined on U, which is a complex plane without these two lines. Why? Because the fundamental group of U is trivial, so it's simply connected. And well, of course, I need to choose a branch of the logarithm, but then I define multiple polylogarithms just in this way. So if you have a string of x zeros, you have the log, powers of the log. And then for any other words, you just define it recursively. So you get iterated integrals. And well, these are well defined because in principle I should specify what's the path, but it turns out that it doesn't matter what's the path because these integrals are homotopy invariant and our U is simply connected. So you can take any path you want inside U. And well, this gives an analytic continuation to the usual, usually defined multiple polylogarithms, which are defined as multiple sums. It's here. Because, I mean, they're only defined in a radius 1 circle. And you can extend these functions even further to the whole sphere without 0, 1, and infinity. But then they're not functions anymore. They're we call them multi-valued functions. So you'll know this. And you also all know what are multiple zeta values. So they're usually defined this way, but they are also the special values of these multiple polylogarithms with this particular kind of words at the point 1. Well, I mean, 1 is outside our domain, but it turns out that for this kind of words, which starts with some x0, then you can actually extend them to 1 without any problem. And they form a ring that I call Z, which is a very interesting ring, and many of you knows a lot about it. So I won't say much. Let me also mention that you can define the special values at 1 of any kind of multiple polylogarithms by some standard regularization procedure using the fact that they have at most logarithmic divergences at z equal 1. Good. And these regularized values are still multiple zeta values. Now, I want to consider the generating series of multiple polylogarithms because, well, you will see it's very important also in other talks to think in terms of generating series. So this is the unique holomorphic solution on U of this differential equation, which is usually called the KZ equation. I mean, you have to have some asymptotic condition at z equal 1 to get uniqueness. And in particular, the special value of this series is what is usually called the Drinfeld associator, which describes the monodromies of this differential equation. And well, there is a theorem of Francis Brown that you can have another solution of this equation, a real analytic solution, with this asymptotic behavior. And I'm not going to construct explicitly this solution, but it can be done explicitly, and it gives, I mean, it can be expanded as a series in all possible words, and the coefficients of this series are called single-valued multiple polylogarithms. So here I'm not being explicit at all because the purpose of this talk is not to talk about single-valued stuff, but there would be a lot to say about it. And let me at least mention that they are constructed as MZV linear combinations of products of the multi-valued polylogarithms. And well, they're called single-valued because, as I already maybe said here, this is a solution on P1C minus 0, 1 infinity. So in this domain, the classical multiple polylogs are multi-valued, but this is an actual function, so it's single-valued. And the simplest example is what happens with the x0. Well, with x0, you just get the sum of log z and its complex conjugate, so it's 2 times the real part, and of course, it's a single-valued. And it's very interesting, the fact that the map SV respects shuffle identities, which are all the algebraic identities in the algebra of multiple polylogarithms. So it's well defined on this algebra, and we call it the single valued projection. And it's related with some very deep stuff in cohomology, and maybe I'll mention something about it later. So now the special values of these single valued multiple polylogarithms are called single valued multiple zeta values. And well, now this single valued projection that you had for the multiple polylogarithms, nobody tells us that it should still respect all the possible identities, algebraic identities between the special values, so between the multiple zeta values. But conjecturally it does, because we have many conjectures, very precise conjectures about the structure of the algebra Z of multiple polylogs, and also about the sub-algebra Z single valued of single valued multiple zeta values. So yeah, I mean, of course, by construction, these guys belong to Z, because as I said, they're Z linear combinations of these kind of products. But they span a much smaller ring. And for instance, it turns out that all the even simple zeta values just vanish, while the odd ones become twice themselves. Good. So now I'm ready to tell you something about string amplitudes. So I'm not going to be very precise about amplitudes because for lack of time and also of knowledge by myself, but the usual idea is to do a perturbative expansion in the string coupling constant, which is considered to be small. And in this expansion, well, it turns out to be a topological expansion, because if you divide the strings between open and closed, and here I'm being very not precise, because I'm considering actually only oriented strings in this talk. Then in one case, for closed strings, you get just an expansion on closed Riemann surfaces with an increasing number of holes. And in the open case, well, you have surfaces with boundaries. So this is, I know they look the same, but this is a disk with 4 points on the boundary, while this is a sphere. And then you have a cylinder, which is considered as a genus 1 object. What you count here is rather the Euler characteristic of the surfaces, but it belongs in the same group as the torus. And well, let's see what happens if you look at genus 0, which is by far the most studied and the most understood case. So you have, let's say you have n+3 string states on your surface, and then you have Mandelstam variables, Saj's, and permutations, rho and sigma. Then you can reduce essentially, I guess, all of the open string integrals to this set of integrals, which just depend on the two permutations, rho and sigma. So sigma exchanges the variables in the path from 0 to 1. So this is an iterated integral. And rho exchanges the variables in here, in the denominator. And let me also remark that you should think of this path as just a circle, and the points on the circle that I've shown before. So this is the boundary of the circle. And the closed string building blocks, well, you have now the Riemann sphere, and rho and sigma, they both appear in the denominator for the holomorphic and anti-holomorphic variables. So it's very instructive to present the 4-point case, because it has all the features, simplified features, let's say, of the general case. So you have the very first integral, 4-point case, so n equal 1. You have only identity possible as permutation. And well, this is well-known function, the Veneziano amplitude, which is expressed as a ratio of gamma function, and have this nice small alpha prime expansion, so for small values of the non-distant variables. And then there is the Virasoro-Shapiro amplitude for the closed string case. Again, this is a ratio of gamma functions, and it can be expanded for a small alpha prime. And you see in both cases, in the expansions, we start seeing multiple zeta values. So these are actually the simple zeta values, the Riemann ones. And there are two observations. So the first one, which is called KLT formula, is that you can express the closed Virasoro-Shapiro amplitude as a double copy of the open one. And the second is that there is a single valued projection between this object and this object. You just map in the expansion, term by term, the zeta values into their images. So the even ones disappear and the odd ones just get doubled. Okay, so now I'm ready to present the state of the art. So, well, I'm not going to be giving everything we know about it, just a couple of things I want to talk about today. So there are the KLT relations we generalize to any number of particles. Then the fact that in the open string integral Z, the coefficients belong to multiple zeta values generalize. This is, of course, a J. So the coefficients of the small alpha prime expansion of the J integrals, which are the closed string ones, are single valued multiple zeta values in general. And even more, this thing that I show you, that you can pass from the alpha prime expansion of the open string integral to the alpha prime expansion of the closed string integral via this single valued projection, is true for any n. And furthermore, there are recursive relations between open string building blocks, which originate from the KZ equation. And so you can get a lot of practical information. You can compute a lot of stuff, and there are many people. So here I've just cited some. I hope all of the people, well, probably some of the people who have contributed to these results, but then there are other things to say. And tomorrow anyway, or some other day, Andrei Kaderli is going to talk about these kind of relations in genus 0 and genus 1. So you will hear more about it. Good. So now let's go to some mathematics. So I want to motivate the definition of elliptic polylogarithms. And to do that, we need to remind ourselves some basics about cohomology, first of all, and then about, let's say, about functions on the fundamental group. So this is going to be the next step. But let's start with cohomology and periods. So you take a manifold, then I hope everyone knows how to define the singular homology groups on the manifold. They're just topological objects, which are defined via this chain complex using the simplices. And this is a Q vector space. For instance, if you take Q coefficients, and you can take the dual of this vector space, and it turns out that it's equal. I mean, it's not a priori equal, but for Q it is equal to the cohomology, singular cohomology of the manifold M. And another group that you should know is the RAM cohomology group of the manifold, which is built out of the complex of smooth differential forms. So you have a derivation, and then you use this derivation to build these cohomology groups. Okay, and then by Stokes' theorem, if you take a class of a smooth form here, and the class of well, and the cycle sigma, then this integral is well defined. Why? Because this is a closed differential form, and so you can view elements of the RAM cohomology group as elements of the singular cohomology group, because the singular cohomology groups are just functions from the homology to well, to Q in this case. And I mean, I want to tensor with C probably here, because the de Rham form will, this integral is going to be complex valued in general. But this is just a way to pass from one cohomology group to the other. And this was, it was demonstrated by de Rham that this gives an isomorphism between the two cohomology groups. So you see, you have to tensor with C here. Okay, and then there is an algebraic version of this story, which is not directly relevant in this talk, but it should always stay there because all what I'm saying, some of what I'm saying can be made algebraic and should be made algebraic. So if you have an algebraic variety over Q, so you should think of a bunch of equations and the solution of the zero locus of these equations, then you can define something which is called the algebraic de Rham cohomology group of this algebraic variety. This is defined with hypercohomology, and I'm not going to give the definition. It's not very important, but for curves, there is a simpler way to define it, and I'm going to define it later because we're interested in curves. And then Grothendieck proved the algebraic version of the de Rham theorem. So this algebraic cohomology is isomorphic to the singular cohomology. Okay, and the same thing hold for relative cohomology. So you can take out divisors from this variety, and you get periods in the sense of Concept-Zagier. And periods are, so you can define them either as the entries of this matrix given the cohomology, or you can define them more elementary as integrals of rational functions with rational coefficients over the domains defined by inequalities, polynomial inequalities. Okay, and the de Rham theorem for fundamental group is now the next step. So we have presented the de Rham theorem for the cohomology groups. There is an analog for fundamental groups. So first of all, let me remind you that the first homology group of a manifold is isomorphic to the abelianization of the fundamental group of the manifold. And this can be seen, and it's convenient for us to see it, as the following quotient. So you take the group ring generated by the fundamental group over Q, and then you quotient by second power of the augmentation ideal, which is just the kernel, which takes any formal Q combination of elements in the fundamental group to their coefficients. You sum their coefficients. Okay, and I presented before the de Rham theorem, and the de Rham theorem tells you that you can describe all of the functionals on the homology group in terms of integrals of differential forms. Now we want to look for homotopy functionals, so functions on the fundamental group, or rather the group ring, Q by 1. And the idea again is to use integrals, but then if you do the exact same thing that you did before, you take a smooth one form, then it turns out that this is a homotopy functional. So homotopy functional means it defines a function on the fundamental group, so it just depends on the homotopy class of a path. And this is true if and only if omega is closed, and it turns out that then it can only detect elements which are in the abelianization of the fundamental group. But the fundamental group in general is not abelian, and so we are missing information on a lot of objects in the fundamental group. So it's just going to be 0 on them. And the solution given by Chen is to consider, instead of a simple line integral, iterated integrals of one forms. So you take smooth one forms, and then if this iterated integral is a homotopy function, so the iterated integral is defined iteratively exactly as I did in the definition of multiple polylogarithms, then it defines a function on this quotient of the fundamental group, and this is non-trivial function in general on any power which is less than R+1 of the augmentation ideal. So in general, with these iterated integrals, you detect more elements of the fundamental groups than what you would detect with just one integral. So of course you can take iterated integrals of length as long as you want. So R is the length of the integral. And so you can pass to the limit, the projective limit of this quotient, and you get this, which is called the pro-unipotent completion of the fundamental group. You shouldn't be scared, just the limit of all these quotients. And then O is just the functions on this group. And then you quotient with C. And Chen proved that, I mean, I've already told you that any iterated integral gives you a function on this guy, but all of the functions on this guy come from iterated integrals, exactly as it happens with the cohomology. And so this is why this is called the Duran theorem from the fundamental group. And it was proven by Chen in the 70s, I think. And again, we're more interested in the relative version of this. So instead of considering loops and one base point, consider rather paths. So you have 2 points and paths between these 2 points. So this is the fundamental groupoid of the manifold. And well, how to compute all these homotopy invariant iterated integral in such a way that we can explicitly describe the pro-unipotent completion of the fundamental group. This is a not so easy question because you have a lot of one forms, a lot of differential one forms. You're not in the quotient, you're not in the cohomology, you're really looking at all the differential forms. And so the shortcut to do this is to use a model. I mean, because of course, if you take just random iterated integrals, they're not going to be homotopy invariant. And what is a model? So you identify a subcomplex of the complex of smooth differential forms, some subcomplex A, which is quasi-isomorphic to the complex of differential forms, which means that the cohomology of this complex, which is induced by the differential, is isomorphic to the cohomology of this complex for any n. And this complex, of course, I mean, this cohomology is by definition the Duran analytic cohomology of M. And the theory of Chen tells you that if you are in this situation, you can look at simply the homotopy invariant iterated integrals of the one forms belonging to A. And they give you all the functions on the pro-unipotent completion. And let me just show you what happens for P1C, which is the Riemann sphere. Well, this is well known. If you take this model, so here I'm writing this as a DGA algebra instead of as a complex, but it's equivalent. So you should think of this as the zero part of the complex, and this is the degree 1 of the complex. And well, these are just 2 differential forms plus the function 1. So this is incredibly easy, but it turns out that it describes the Duran cohomology of the Riemann sphere without 0, 1, infinity. And well, okay, but then it means that homotopy invariant iterated integrals of dz over z and dz over z minus 1, which are polylogarithms, multiple polylogarithms, describe all of the functions here. And we call them the periods of the fundamental group, base point 0, z. This is kind of, a priori, it's an abuse of terminology because with Chen's construction, nobody tells you that these guys will be actual periods for our definition, but it turns out that this rational model is algebraic enough to get us actual periods. Okay, so now I want to say something about compact Riemann surfaces, because we are going to focus on compact Riemann surfaces, and we know a lot more things on Riemann surfaces. And by the way, it's quite a special situation also because they're both algebraic curves and complex manifolds. So you take a genus G Riemann surface, you should think of them as donuts because I'm taking G bigger or equal than 1. And then you take these, I mean, you know that the fundamental group is constructed this way. And then the abelianization of this is just Q to the 2G. And well, I define an algebraic one forms of the Riemann surface. So this is an abuse of terminology actually, but I define them to be the meromorphic differentials on the Riemann surface. And then you probably know that there are first kind, second kind, and third kind meromorphic differentials on a Riemann surface. So first kind of the holomorphic ones, so those which span actually, which give the H10 of the Riemann surface. And then there are also second kind if they're meromorphic with no residues. So first kind is contained in second kind for me. And I define H1, the RAM algebraic of the Riemann surface, to be the vector space of second kind differential quotient by the exact differentials, which are, I mean, D of some meromorphic function. M of X is the field of meromorphic function on the curve. So this is my definition, but it turns out it's a standard definition which came much before Grothendieck's definition of algebraic de Rham cohomology, when people were studying only curves, because this can be done completely algebraically, so you don't need to have the complex structure on the Riemann surface. You just take an algebraic curve and you do the same. And then there is the theorem of Grothendieck, which is true also with this algebraic de Rham cohomology. And well, you still do you still prove this by integration, but now this is well defined. Why? I mean, if you have singularities, you don't want your path to give you a different result if you pass on the left or on the right of the singularity, because then your integral wouldn't be homotopy invariant. But it's well known that you can avoid problems if your residue is 0. So by the residue theorem, if you take second kind differentials, you get a well-defined integration. And an algebraic, there exists an algebraic version of Chen's theorem for curves. This is very important. I think it was proven first by Richard Hayne. That tells you that if you do this for iterated integrals, so there is a concept that you can define iterated integrals of the second kind, whatever this means. I mean, you just take second kind differential forms and then homotopy invariant integrals of this second kind differential forms. We call them iterated integrals of second kind. They have to be homotopy invariant. And then they're also describing all the functions on the pluripotent completion of the Riemann surface. This is another way of constructing the periods of pi1. And let me briefly mention that in general, in string theory, but I think in general also in mathematics, you're rather interested in configuration spaces of points on these Riemann surfaces. And this is my notation. So you have a Riemann surface, possibly punctured, and the configuration space of n points is just defined in this way. And well, the fundamental group, for instance, of these configuration spaces is well known and well studied in mathematics, related to the theory of great groups. And if you do the exact same game of that we have made with just one single Riemann sphere, with n points on the Riemann sphere, you get the multiple polylogs in several variables as periods of pi1. Okay, so yeah, let me briefly also mention that beyond genus 2, the description of the cohomology rings of these configuration spaces is not very explicit, and so it's a priori hard to build models. And I told you that models are quite important if you want to construct all the periods of the fundamental groups. So this is probably the main difficulty in extending the theory of multiple polylogarithms beyond genus 1, let's say. But then let's take a look to genus 1. So this is the main part of my talk. So we want to look at a complex one-punctured torus. Why just tori and not general genus 1 Riemann surfaces? Because it turns out that all closed Riemann surfaces of genus 1 are complex tori. And well, one punctured is just something that you naturally find in string theory, for instance. But it's also very natural from the viewpoint of considering the moduli space of these guys. So you take from now on tau in the upper half plane H, so the imaginary part is positive. And then you have a complex torus that I denote T, tau, which is just given by C quotiented by this lattice. So as I said, these are all the genus 1 Riemann surfaces. And then I want to take out the identity 0 of the torus, and I will denote the one puncture torus this way. Then you can, I mean, it's well known that the fundamental group is abelian for the torus, just Z2. And if you take out one point, it's not abelian anymore. So it's just free group on two generators, which are the cycles A and B, usually called. And well, of course, the first homology group is going to be equal to this in both cases, because you see the abelianization. And the second homology group, on the other hand, is going to be trivial in the case of one puncture torus, while it's not trivial for the full torus. And then you all know, I'm sure, the Weierstrass function and the Eisenstein series, but still let's give this definition. So this is the Eisenstein series of weight k. It's a modular form of weight k, entering the definition of the Weierstrass function, which is defined, for instance, in this way. So as a in a neighborhood of the origin, as a meromorphic function with a double pole at the origin. And it turns out it's well known that the functions on the punctured, so the rational functions on the punctured torus, are just polynomials in the Weierstrass function and its derivative, with, of course, relations between the Weierstrass function and the derivatives. Good, so let's go to the RAM cohomology. So first of all, if you consider the algebraic RAM cohomology, well, it turns out, everyone probably knows that it can be described via the first, these two differential forms, dz and Weierstrass function times dz. So they correspond to dx over y and x dx over y if you think of an elliptic curve instead of the complex points of the elliptic curve. And well, it's also well known that, by the Duran theorem, you can integrate over the cycles, which in this case, the generators are the cycle A and the cycle B of the torus. And you get periods. Well, in principle, you would get periods if this construction I gave was algebraic. This is not quite algebraic, but it can be made algebraic. But let's say you get periods using these differential forms, which are 1 and tau, and quasi-periods using this other differential form, which turn out to be G2, the non-modular weight 2 Eisenstein series, and 2 pi I plus tau G2. And the analytic RAM cohomology of these guys, well, is much simpler. It's just generated by dz and dz bar. Good. But we know that the analytic and the algebraic RAM cohomology must be isomorphic, because they're both isomorphic to the singular cohomology. And one way to see this is, for instance, to identify the dz bar differential form to a combination of these two differential forms via this equation, which is, I guess, quite classical, and which allows you to, since this is just a total differential, so it's something that vanishes in the cohomology. And so you see that the class of dz can be expressed in terms of class dz and P of Z is Z. Good. So now we know a lot about complex tori, and we are ready to construct interesting stuff on tori. So let's talk about the Kronecker function, which was introduced in the 19th century and then found many applications in the last 30 years. So let me define zeta as this exponential and q as this exponential. And well, this is just quotient of the odd theta function with the eta function. So let's just define this function theta this way. And then you want to set, so this is the Kronecker function. You want to set this quotient of theta functions. So we will consider z as a point on the punctured torus, but alpha we will rather consider it as a formal variables. And of course, both these functions still depend on the modulus tau of the torus. So this is a multi-valued function on tau star. What does it mean multi-valued on tau star? It means that if you just continue it analytically along the cycles, spanning the generating the fundamental group, then is not going to be invariant. And indeed, I mean, along the A cycle, so if you take Z plus 1, it remains the same, but along the B cycle, so you take f of Z plus 2, then it's going to give this monodromy. And furthermore, it has a simple pole at Z equal 0 and no other poles on the torus. So we can formally expand this function f and the coefficients of these expansions called Gn, traditionally in physics, are certain holomorphic, well, not holomorphic, meromorphic functions on the complex plane, which are not quite functions on the complex torus because, as I said, this is a multi-valued generating series. And let's see what they are. So G0 is just 1. G1 is, well, it's just presented in this way, for instance. There's a simple pole at Z equals 0. And then it has an expansion in terms of Eisenstein series. And it can be also written in terms of the, this is the Weierstrass zeta function. It's not the Riemann zeta function. And for a higher n, well, you get functions which are actually holomorphic at Z equals 0. And they belong to this ring. So they're rational functions in here. So Weierstrass function and derivative of Weierstrass functions. And you add polynomials, I mean, you had powers of this G1 function that is in here. So a priori, it could have poles at Z equals 0, but it turns out they don't. And the first definition of elliptic multiple polylogarithms, which we have already seen in Britto's talk, is this one. So you take these kernels and you consider an iterated integral. So at 0, in general, there will be problems, but you just regularize in the same way as always. And I want to stress here that Z is in C. So I'm considering these as one forms defined on C, and these are iterated integrals on C, and they are homotopy invariant. So this is well defined because these guys are holomorphic outside the, they are meromorphic. And so why should we call these guys elliptic multiple polylogs? Well, this is kind of natural to do in string theory. Also, if you take the limit as tau goes to infinity, you get genus 0 multiple polylogarithms. So in general, you have an asymptotic expansion for tau going to infinity, and the coefficients will be just the genus 0 multiple polylogs, which is quite nice. And then I will give other motivations later. Anyway, this is probably the best working definition in string theory for sure, and possibly also in quantum field theory. The Brown-Levin approach now to define, to give an actual generalization of the multiple polylogarithms in genus 0 is to consider this correction of the form f. This is the Kronecker function from here. And then you want to multiply by this function, which is non-holomorphic. And then you get a well-defined function on the punctured torus, because it turns out that this 2 pi I times this guy has precisely the right monodromy when you go along the B cycle, because it gives a plus 2 pi I, but you can see here you got the monodromy a minus 2 pi I, and they cancel out. But it's real analytic, it's not meromorphic anymore. And a theorem of Brown-Levin is that, I mean, you can expand again. So this is a form now, not a function. I've added dz. So you can think of this as a generating function of one forms, omega n, and define also the one form 2 pi I d of im z over im tau. Well, you can construct, using these forms, a model for the RAM analytic cohomology. The RAM complex of the torus. So you just consider this in degree 0, 1, and then in degree 1 you consider you put inside your model all of these, so infinitely many forms. It's a lot of stuff. It's much worse than genus 0, but it's still much better than considering all of the possible one forms that you have on a punctured torus. And it turns out that this gives a model. And in particular, you take the first, I mean, this form and this form, omega 0, which turns out to be just dz, and they give a basis of the first cohomology group. So, I mean, to prove that it's a model, first of all, you should check that you get a 0-second cohomology group. And so you need that the wedge product of these forms, it's again the differential of some of these forms. And this turns out to be true. So, and you can do the same for a configuration space. And then a second definition of elliptic polylogarithms by Brown and Levin is that you take this form. Now I've added also this guy, and I'm doing something more formal than before. So I'm also adding into the business these two formal non-commutative variables. And this is now valued in the completion of this free Lie algebra on these two generators. Then it turns out that that this form, I mean, you can integrate it. You can do iterated integrals of the forms in here, and the coefficients of this very formal series here, which will be iterated integrals, special iterated integrals of these forms. It turns out that they generate all the periods of the pro-unipotent completion of the punctured torus. So this is the right mathematical definition in some sense of elliptic polylogarithms. But in fact, it turns out that you can in practice write these guys in terms of powers of the imaginary part of z and the meromorphic functions introduced before. So this is one more motivation for calling these functions gamma tilde elliptic polylogs. Okay, there is another approach which I must start hurrying. So there is another approach by Levy and Racinet. They construct a different correction of the function f. So they multiply by this exponential. Okay, why? Because it turns out that you still get a well-defined function on the punctured torus. So you are defining a single-valued function because this function g1 has also the right monodromy along the B cycle to compensate for the monodromy of f. And why do we have two different ways? Well, recall I told you that you have this equation. And then this equation implies that if you take the class, so you take this dz pi over im tau on this side of the equation, then you take the class in cohomology. And then you have this identity in cohomology of differential forms. And well, it turns out that the periods of this guy and the periods of this guy then must be the same. And the B period, so the period of these two forms over the B cycle, which can also be thought as the monodromy of the primitives, are the same. And the primitives are nothing but, well, the completion of Brown-Levin on one side and the completion of Levin-Racinet on the other side. So it's not just two random functions that you take to complete your Kronecker function. It's just these two are quite special. And Well, what do? You also expand this function that I called h, and the coefficients now are second kind differential forms. So we're now on the algebraic side of the story. And again, algebraic, I'm not really making it algebraic. I'm still considering Riemann surface rather than the algebraic curve. And by Einstein's theorem, the periods of pi1, but then now I don't want to take 0 as one of the points, are all the homotopy invariant iterated integrals constructed with these second kind differential forms. So I've constructed in a different way the periods of the fundamental group, except for the fact that now, while these functions don't have a regular, don't have a simple pole at 0 anymore, they have horrible poles, and so you don't really want to put a 0 in here, and so you cannot really get the same kind of functions near the mark point. So there are ways. So this is just what I just told, I think. So you construct. I mean, you have to construct this connection formally in x0 and x1, and then the periods are the coefficients of this formal series. But there is a way around the fact that you don't have these simple poles at 0. This is a different story. There is an article by Ma Luo, who constructed a really algebraic version of elliptic polylogarithms, but he was forced, because he wanted a simple pole at 0, to add other poles in other points of the curve. Good. And let me very briefly mention that there are other approaches. So a classical one, which is just considering averages of the classical genus 0 multiple polylogs. And related to these, the ELI functions. And algebraic construction by some physicists who consider iterated integrals using integration kernels with at most simple poles. So they were not quite defined on the elliptic curve again, but they generate the same space of these guys. And they're also related to constructed all the primitives of rational functions on elliptic curves. And all this class of elliptic polylogs, which have their pros and their cons, are related. So, you can take special values of elliptic polylogs, but the way Enriquez defined them is a little bit different. So Enriquez defined elliptic multiple zeta values by considering the two cycles separately. So on the A cycle, you just consider the special value of the gamma tilde, and on the B cycle, you just consider the modular transform. And the upshot is that this definition was motivated by the fact that there are coefficients of an elliptic associator, so an analog of the Drinfeld associator, associated with a KZB connection, which is the analog of the KZ connection. But you will hear more about this in Kaderli's talk. And well, they're pretty nice functions related to multiple zeta values and iterated integrals of Eisenstein series. I'm not going to talk about this. I have to be very brief now. So genus 1 amplitudes have to do with elliptic polylogs. Why? Because you consider these kind of integrals over moduli space first and configuration spaces of points on the torus second, defined in terms of the Green's function on the torus. And if you only focus on the configuration space integrals, so you get rid of this integral and also of this function, which doesn't really matter for the mathematics, then you have that your closed string prototypes become these kind of iterated, well, this kind of multiple integrals, and the open string, this kind of multiple integrals. These integrals for closed strings are called modular graph functions, and they're very well known, and Eric Docker is going to talk about them tomorrow. And the open string integrals, where they are given by iterated integrals of functions which are very closely related to the kernels of the elliptic polylogs. And so what's the state of the art, very briefly? In genus 1, the coefficients of the open string integrals are A elliptic MZVs and the modular graph functions that I've mentioned in the closed string case are a very interesting class of functions, apparently related to the open string integrals by some single values like projection, and more concretely related to the elliptic MZVs because they are combinations of holomorphic and anti-holomorphic elliptic MZVs. Moreover, there are also relations between genus 0 and genus 1, so this is a whole different subject, and this was proven in n = 2 or for open strings for NEM. There are recursions also in genus 0, this will be in Carol's talk, and it's not known how to construct KLT relations, and there are partial results also for this modular space integration that I didn't talk about, and here there are names, but I'm sure this is not the whole list. And so in the -3 minutes that I have, I must say at least 2 words to conclude about beyond genus 1. So beyond genus 1, there are results in closed string theory. So there was a construction of higher genus analogs of modular graph functions, and they appear for sure for G = 2 and possibly for genus bigger than 2. We will learn something more with Eric Docker. And the hope expectations is that the nice things that we have seen at genus 0 and that seem to generalize at genus 1 should hold for any genus. This is what physicists seem to believe. So KLT relations, which are in some sense the same as single value projections because of twisted cohomology business that somebody else is going to talk about in this conference. And if somebody is interested, later I can, in the question time, I can say something about a possible strategy, which is a work in progress with Benjamin and Ricketts, on how to construct higher genus analogs of polylogarithms, which is something that people would imagine will show up in open string case for G bigger or equal than 2. So I leave the slide here and I stop, and I'll be happy to comment more about it. So thanks for your attention.
Thank you very much, Federico. Again, let's all take 2 seconds. We unmute ourselves, and then we give Federico a well-deserved round of applause.
Oh, yeah?
So I see that there's already a first question by David Waterst. David, please go ahead.
Thank you, Federico, for this overview. My question really arises first at genus 1, and in your maths background, you had a crucial slide that said, shortcut, choose a model. Could you go back to that? Yeah, and so what I see at the bottom of that is a rational model for the projective line -3 points of iterated integrals of dx upon x and dx over 1 minus x, which I understand. The puzzle I have is, to me, that is the model. Could there be some other model? And if so, how would it be related on the side of analysis? And I guess that question then continues non-trivially at higher genus.
Federico, you're muted. You're muted, Federico. You have to unmute yourself.
Do you hear me now?
Yes.
Sorry. So yes, you can construct different models in general because, I mean, you can even construct models which are related by, related by chains of quasi-isomorphisms that are not directly related to each other's. And then about the fact that it's a rational model, so I wouldn't know. I wouldn't know, actually. I never thought about constructing a model yet in my life, but there's probably somebody else in the audience who can say something else. But in general, there are more models for the cohomology, I believe.
But,
there are minimal models. This looks kind
you see,
minimal model to me.
Yeah, you see, I wanted to change that little word "a," which you've chosen rather carefully, into the definite article "the," and you're telling me that I can't because there's something that you don't know that could equally do the same job.
Yeah, so I believe, so I believe that this is the minimal model that you can choose, but in principle you can have more stuff which gives the same exact cohomology groups. So this is the best model for sure for P1C, I would say.
Thank you.
More questions? Yeah, Niels.
Hi, Federico. Thanks for a very beautiful overview talk. So just a remark, could we maybe go back to the very last slide of yours with the overview?
Sure. Here.
Yes, right. So just to add to this, because I don't think it's very well known and also not very well documented in the literature, but there's actually a third approach I mean, besides the real analytic approach of Brown and Levin and the meromorphic approach of Levin and Racine. So there's a third approach, which is purely algebraic and uses only forms of logarithmic poles, but you have to pass to a cover of the elliptic curve. And this cover is known as the universal vectorial extension of the elliptic curve. And so you're somehow changing the geometry a little bit. So you're passing to a cover of the elliptic curve, which is actually an affine bundle. So it's not a big change you're doing, but then this has the pleasant side effect that you can have your cake and eat it, so to speak. So you can work with, you can kind of work on the elliptic curve as it were P1 minus 3 points. And yeah, so this approach I think goes back to, as far as I know, to a letter that Deligne wrote some years ago to Dick Hayne and also to Ettinghoff and Enriquez. And yeah, but I don't think it's that well documented in the literature. So I believe Enriquez and Ettinghoff, they wrote a paper partially realizing Deligne's vision. And well, since you're working with Benjamin, you can surely ask him about this. You probably know which paper I mean. But just to say that there's a third approach, which is in some sense, well, which is purely algebraic, that is an advantage. And the shortcoming is that, well, you have to complicate the geometry somewhat.
Yeah, thanks a lot. Yeah, I am aware of that. But I mean, for reasons of time and also for my personal ignorance on that approach, I wasn't thinking of including it. So thanks a lot for mentioning it.
You should really check it out, because another reason I think this will be interesting for Claude and collaborators and Johannes and these other people, it's very closely related actually to their approach, because what they are doing kind of, if I recall correctly, is they work with a primitive of the P function, like a Weierstrass-Zeta function, and that's not exactly algebraic. I mean, this has a non-trivial transformation behavior, but if you pass to the universal vectorial extension, you can actually subtract this non-trivial transformation behavior, and you get actually that the Weierstrass-Zeta function gives you a well-defined differential form on the universal vectorial extension. So I believe that this is a way to make the considerations of Britto, Dewar, and Tancredi and others purely algebraic in the strong sense. So yeah.
Yeah.
Just putting this out there.
No, thanks a lot. I will take a closer look. Thanks.
Okay. Well, thank you, Niels. And this is very interesting. If you want, and you have any kind of reference or just like hints of names of where one could find information, maybe you can put it on the chat.
I'll happily do that.
Then there's a question by Piotr. Or on Slack. Hi. I was just pointed out to me that one could also put it on Slack.
Actually, it's a question to both you, Federico, and Niels then. So this third approach, is that like analogous to, okay, it's a physics question. I didn't quite understand the math of this particular point. Is this like is this universal cover related to having loop momentum in the, if you guys are familiar with that framework? Where you also have some sort of a universal cover because you cut your surface open, you cut it on the A cycle, and every time you cross this A cycle with the particle, it's like you're going on you're shifting some, like the value of your loop momentum by an integer unit. So you're kind of going on a cover of the surface. Is that, am I making sense to you? Or I guess I can just look at the reference that you will put on Slack or to make my mind, but I just wanted to ask you your opinion.
Yeah, what's certainly true is that there's some kind of universal cover of the elliptic curve in a algebraic sense. Yeah, I don't know what loop momenta, so maybe you know, Federico.
Okay, yeah. Okay, I'll ask you.
No, I wouldn't know too. Sorry.
Okay, thanks, guys.
Okay. Are there more questions? If not, then I think we can all thank Federico again. But before you leave, I think Matt wants to say a few words about what is going to happen tomorrow morning.
Yes, so we're going to be having a discussion session tomorrow morning as sort of a jumping off from the talks of today. There have been some approaches that have been very mathematical and geometric, and there have been some approaches that have been much more geared towards the particular details of how to solve a differential equation for particular integrals and hashing out efficiency concerns. So what we'd like is sort of a dialogue of seeing how the two different kinds of approaches can inform each other, how different people along that spectrum can give insights that the others can use. But anyway, just sort of as a jumping off point. So we welcome those of you who are interested. It's 11 a.m. Central European time tomorrow.
Okay. So if there's anything else you want to comment on, if you want to ask questions, have discussions, please feel free to use Slack. And also, I guess, feel free to hang out here if you want to discuss a bit more. And otherwise, I guess we see you all tomorrow morning, either at 11 for a discussion session or at 2 for the next series of talks, where tomorrow we will explore a bit more the relationship between elliptic polylogarithms, elliptic zeta values, and string theory. See you all tomorrow.